Okay, so it's about 1:02. Thought we'd go ahead and get started. So I'm excited to give some opening remarks here with my friend and colleague, Paul Nagy, about some of the data science initiatives at the School of Medicine. And it should be underscored that many of those initiatives have kind of already been in partnership in some regard with Dr. Zaleh and IDEIES as well. I thought I invited Paul Nagy to come, and because I think he's closer to this precision medicine analytics platform, which I thought would be very timely to discuss here. So with no further delay, I'll let him start, and then I'll close out with a couple remarks about some data sets and that we are proud to be developing over the next few months.
That's great. Alex, thank you. Can you see my screen?
Yes, I can.
Perfect. It's great to be here. Thank you for the invitation. My name is Paul Nagy, and I'll be talking about our precision medicine effort and how we're trying to enable reproducible research off of medical record patient data. So the PMAT platform is an initiative at Johns Hopkins Medicine to build a secure environment where we ingest all of the clinical data from our patients within Johns Hopkins Medicine, and then provide analytics tools for researchers to be able to work on that data to conduct research on treatment effect and looking for new phenotypes that help predict the progression of disease. So the platform is sitting on the Azure cloud. As part of this, we have ingested data from our clinical information systems within the Johns Hopkins Medicine system. They include our electronic medical record, which has over 2.6 million patients over the past 5 years. We have over 85 million medical images taken from radiology and cardiology. We have physiological monitoring from 2,700 beds streaming from throughout the health system. And we also have sequencing data that Alex will be talking to you about in just a few moments. So it's not just providing the data, we also provide data services on it for harmonizing that data into common data models, for providing a data catalog, for enabling search and honest brokering it, where we want to protect patient identification purposes as much as we can, as well as providing annotation and pre-processing environments. So we perform patient matching across these different data modalities, and then provide that to the researcher on the PMAT platform. And we do that through a combination of different analytics environments. The first one is the SAFE desktop. The second one is we have Alex Zaleh's server environment set up within our environment, where we have over 600 data scientists who use that with a combination of R and Python containers. And then with that, we have pointed to that a different compute environment that we can a shared resource node that they can use, as well as we also have a high performance compute cluster within this environment. This entire environment is sitting within the Johns Hopkins Medicine environment. We have authentication, authorization, and availability monitoring, and accounting all driven on top of this platform. So the data stays in the platform, the researchers come in, they can perform all their analysis and extract their aggregated results. This is what the platform looks like. In the back end, we're doing a lot of data manipulation and moving with a lot of stored procedures within, whether it's SQL. We also we bring in ingest NoSQL data like narrative notes into this process. And what I wanted to quickly share is one of the most important data sets we now have on our precision medicine platform is a data set called OMOP, which is driven by the Odyssey community, which is an open science community standing for observational health and data science informatics. And what we've done is we've taken our proprietary EMR data, our patients, our 2.5 million patients with our 23 million visits that we've performed 14 million procedures on, and we prescribed over 40 million medications and have diagnosed 65 million symptoms on the patients, as well as performed over 400 million labs. We've converted this data into common terminology concepts that have been standardized, and we have mapped them into a common data model. And now this gives us a data set which is really powerful. So when we perform analysis on that data, whether it's complex cohort identification or treatment effect analysis, we can do it in a way that we can actually perform research and then share our code with other institutions around the world. So we have, across the world, we now have mapped over 10% of the world's population into the OMOP data format. And so we now have access to over 800 million patients throughout the world, through our research network, that all use the same data format. And so this is really exciting for us because we have 2.5 million patients, but whenever you're doing a rare disease, you always end up being limited by the number of patients that you're looking for subsetting. And this enables our researchers to start their research here at Hopkins and then be able to combine it with data throughout the world to be able to conduct very large network studies. What's really exciting about this really enables reproducible research, in that it's not just the data that's in a common format, but how we define the cohorts using complex temporal and Boolean logic is an expression language that's in JSON that actually is now computable. So whenever we publish a paper, we can publish complex phenotypes as well as their data characterization in a common format that other people can quickly reproduce. And this is a big step in making observational research into a much more harder science, and being able to allow reproducibility across different health systems and allow this evidence really to be able to be disseminated widely. So this is an exciting step. And so whenever we do studies now, every step that we do, from specifying our protocol, defining our concept sets of what represents the outcome cohorts or the treatment cohorts, the phenotypes for defining our cohort definitions with our inclusion criteria and exclusion criteria, along with even the study packages that we use for characterization and prediction, are all things that we can now share on GitHub and share in a way that it's all in the computable format. Even we have aggregated results viewers that we can do. So this whole step now is something that we can make transparent to enable repeatable science. And so just want to quickly share. So this is so it's been exciting to see the precision medicine platform grow. We now have we have 600 data scientists working on our Sci server environment, and over 6,000 scientists working within our safe desktop, being able to look at this data and be able to make new discoveries around it. Last year, during our COVID research project, we had over 200 clinical research teams studying our data on PMAP, looking for trying to understand the progression of disease for COVID and studying different treatment effects. Alex?
Thanks, Paul. That was really great. I thought it'd be a nice update, really great progression on PMAP. I look forward to engaging it in the future. Some additional data science and data generation initiatives that I thought would be relevant to share would be our work at the Cancer Center, where we've been trying to aggregate real-world cancer genomics data. It's great to have seen over the last few years, maybe almost decade, really a high degree of integration of genomic testing in our routine clinical care. And that's why I use the word real world, and similar to some of the way that Paul was talking about as a common thread observational data, where we're not necessarily talking about clinical trial data, we're talking about the data we're seeing in our routine care. And so we're trying to associate that data with clinical assessments and also tumor staging and prognosis, and put that together into a data set that has two views to it. It has a data analyst light view, which is more a web portal that's enabling maybe the person whose domain expertise is more in the biological sciences or in medicine to take a look at the data, ask questions of it in a kind of cursory manner, but then be able to pass that question down to maybe a data scientist and engage the data more thoroughly. That portal is accessible from our internal campus JADES Genomics site, which is where the testing is done. We can see basically tumor types, outcomes data, mutations, and you can basically use this portal to ask questions of the data. Does a certain mutation type have a certain outcome association? Or does a certain outcome association have an association with a molecular or a staging parameter, for example? And what it potentially allows us to do is, if a set of patients are more deeply curated in terms of they have multiple different outcomes, we might be looking at some things that actually Paul was talking about in terms of richly curating them in a common format, if we can get there for some of these patients, we can start to do a lot of interesting correlatives. We are about 10,000 cases. We do about 2,000 cases of sequencing here in-house per year. And we expect this to continue to grow as sequencing becomes more and more common for this. Another brief thing I wanted to bring up is imaging, a topic that may be near and dear to many folks' hearts. Pathology is just beginning its journey of looking at a tissue in the microscope in the analog to converting it to a digital image to enable analytics. And we're really jumping into this. We have a publicly facing the Johns Hopkins Surgical Pathology Unknowns. It's a collection of cases that each week the attending physician puts together difficult cases. Diagnoses are annotated and put online and made publicly available to the world. These images are gigapixel images, very high resolution images. We also have used these platforms for curation of research cases, even now in 3D, as you can see here. So these are 3D images from pancreatic cancer biopsies or cytology. Now, I guess the overarching theme from the kind of this quick view into the data science initiatives update is that we are very excited to be generating as many high quality data sets as we can. And we are, as much as possible, actively engaging with all our data science colleagues across the different departments of the university here and the hospital, and internationally as well. So it's an exciting time, and look forward to hearing the rest of the talks today. Thanks so much for your attention. And thank you, Paul, again, for coming to join us such short notice. Appreciate it.
Okay. So good afternoon. I'm Janis in Chemical Engineering and Applied Math. And it's a real pleasure to introduce Rebecca Lindsey, who is giving one of the keynote lectures. We did go to the same grad school in the University of Minnesota, but then she was a postdoc and then is now a staff scientist at Lawrence Livermore. And I want to say a couple of things about her and her work. First, it's the third time I hear her speak, and I still hope that I will see her in person sometime at Hopkins, like, you know. The second thing is, in her work, she has worked on, for example, chimes, which is a Chebyshev-based potential that includes also Turner interactions, and importantly, in how to get data to train something like that, which I expect is something she will tell us about. But she also has worked on, for example, nucleation of carbon when you have shocked extreme materials. And in addition to the things I normally know, I looked up her website at Lawrence Livermore, and I found the following statements. First, every year she tells herself, 5 years ago, I would never have guessed I would be working on this. And second, she says, talk to everybody, do at least everything once, and don't be afraid to ask questions. So you will talk to everybody, and we will not be afraid to ask questions. Welcome.
Well, thank you for the wonderful introduction. Let me share my screen. Let's see here. There we go. So again, yeah, thank you for the introduction. It's an honor to be invited to speak at this symposium. So today I want to talk about some of the efforts my teams have been putting forth toward leveraging data science to understand materials under extreme conditions. But before I jump into that, I want to take a few minutes to just sort of motivate why we work in this problem space. And so to a large extent, this comes down to the fact that we work within the Energetic Materials Center at Lawrence Livermore National Lab, where our goals are to understand the fundamental science of energetic materials, or explosives, to help try to improve safety and reliability and performance of these materials, aid in stockpiled stewardship, non-proliferation, and counterterrorism efforts. And so a good portion of this work entails developing advanced experimental and computational tools where we aim to probe material evolution under the conditions realized in detonations. And so this is typically going to fall in the regime of roughly a few thousand Kelvin and a few tens to hundreds of gigapascals. And so in my biased view as a chemist, this is kind of the thermodynamic sweet spot for interesting phenomena. So things are moving around fast enough to start reacting and undergoing interesting physical phenomena, while at the same time not being so hot that everything just sort of dissociates into a plasma. And so from a practical standpoint, that means that these conditions are relevant to a myriad of applications beyond just the stockpiled stewardship work that's kind of our bread and butter. So for example, we work in trying to understand things like planetary science and nanomaterial fabrication, prebiotic chemistry, and things like chemical safety. And so all of this to say there's a preponderance of interesting science to do in this area. But one of the problems that we face is that the experimental and computational studies are made more challenging by the sort of confluence of complicated materials, extreme and dynamically changing conditions, and the high cost associated with running our physical experiments and their destructive nature. And so today I want to talk about some of my team's efforts to develop predictive modeling capabilities to overcome some of these challenges. And so specifically toward things like material aging and compatibility, where we're trying to develop improved models that can help us understand how material aging is going to impact their performance. And then I'll also talk about some of our atomistic simulation efforts, where here we're trying to understand the microscopic phenomena that govern the response that we see as materials evolve under these extreme conditions. And so ultimately here, this work is sort of shares in common the fact that it relies critically on data science as sort of a tool. And so I'll start off by talking about our atomistic simulation efforts, which is done in collaboration with the team listed here. So let's start with a bit of background and motivation. So within the Energetic Materials Center, we rely critically on continuum modeling capabilities. And so this is a sort of simulation that can achieve quite large scales, both in time and length. So ranging from perhaps a micron and microsecond for a single material, all the way out to the meter scale and beyond. And so we really like to use this as a means of guiding and aiding in interpretation of these challenging physical experiments, where we're trying to perhaps get at the phenomena that govern the response that we see, and oftentimes to forego these experiments altogether. Now, these simulations are input greedy, so we're going to need to provide models that describe the equation of state, thermochemistry, and dynamic response of all of the different materials that go into them. And so traditionally, these sort of models tend to be generated through parameter sensitivity studies. So one will select an empirical model form, tweak the parameters, run a continuum simulation, make a prediction, and then try to compare that with some experimental data. And if it doesn't match, you go back, you tweak the parameters, and you kind of rinse and repeat. And so this has a few disadvantages associated with it. First, oftentimes the experiments needed to validate these models are expensive, so we can be working in a sort of data-starved regime. But more importantly, this approach tends to preclude validation of the physics that are assumed in these models. So that really becomes a problem when we think about using these in a predictive capacity. And so to overcome this challenge, we've been really interested in multi-scale modeling as an alternate means of generating physically motivated input to these simulations. So what I'm showing here is a very, very coarse view of this multi-scale modeling framework, where the idea is instead of starting from experimental data, we can start from data generated from higher resolution or atomistic simulations. And so this approach is nice because atomistic simulations themselves require very little in the way of input. We really just need an initial set of coordinates. So this can be like a crystal structure for our material. And then some sort of interatomic model that tells us how the system energy is going to change in response to these atoms wiggling around. And so with this and Newton's equation of motion, we can predict how the system is going to evolve over time, and we can post-process these simulations to get at things like the dynamics, equation of state, and thermochemistry for these materials, where this happens to be precisely what we need to input to our continuum simulations. And so we can feed these in, run our continuum simulations, generate the predictions we were trying to generate before, and of course, validate these with experiment if we like. And so as presented, this is kind of seems like an ideal approach. but I've glossed over a critical detail, which is the critical role that the interatomic model plays. And so the idea here is that any errors introduced by this model are going to propagate up this input chain, potentially exacerbating and compromising the predictions that are coming from our continuum simulation. And so we spend a lot of time thinking about this question of, how does one select a suitable interatomic model for these sorts of applications? And so traditionally, we've had two different approaches available to us. We could use quantum mechanics-based models, which are going to be very, very accurate, but these are also very computationally expensive and so limit us to prohibitively small system sizes. And so then on the other hand, we have molecular mechanics approaches, where comparatively these are extremely computationally efficient. But here the challenge is that these models tend not to be designed or parameterized for the materials or conditions that we're interested in. And they are also very difficult to tune and generate parameter sets for, because these are very highly nonlinear models. And they also tend to be confined to lower levels of accuracy than quantum mechanics. And so ultimately what we needed was some approach that could bridge this capability gap, giving us the predictive power of first principles, or quantum mechanics, if you like, and the computational efficiency of molecular mechanics. And so this drove us to become interested in this idea of leveraging machine learning as a way to generate models for our applications. And so in the next couple of slides, I want to talk about the approach that we've been developing to do this. And so our interatomic model is called CHIMES, for the Chebyshev Interaction Model for Efficient Simulations. And as you can see here, CHIMES is a generalized many-body model. So our total system energy is going to be described as the sum of energies for dimers of atoms and trimers of atoms and tetramers out to arbitrary bodiedness, where we use the following generating function to write down these many-body energy terms. And so this is just telling you two things. So the sum over this ty chunk here is just telling you that we construct our interactions from Chebyshev polynomial series. And then this product symbol here is telling you that we treat our many-body interactions as the product of interactions for constituent atom pairs. So for something simple like a two-body interaction, we have the following. So each polynomial, or each t, is a polynomial of subscripted order. This argument S is just the transformed pair distance between a set of atoms, I and J. And then these coefficients C out front comprise the fitted parameters of our model. And so at this point, there's just a few takeaways. The first is that we're not really making any assumptions about the physics of the system that we're trying to describe, but instead choosing to impart a high degree of flexibility in our models so they can learn the topography of our target potential energy surface. And then the other sort of key feature here is that our models are parametrically linear, so in these coefficients C. And so to fit these models, we work in a nominal force matching framework. And so the idea here is that we're going to generate an initial training set by running quantum-based atomistic simulations. And these simulations are going to give us what we call frames containing coordinates for all of the atoms in our systems and the corresponding forces on those atoms. And so provided this information, we can try to fit our model by minimizing the following objective function. And so all this is saying is that we want the forces on each atom predicted by our model to be as close as possible to what our quantum-based reference method is predicting. Where it turns out, because our models are parametrically linear, we can rewrite this in the following matrix form, and now we are free to use our favorite linear solvers, which are going to let us get at solutions very rapidly. And so for this slide, the takeaway is that these models are rapidly parameterizable and capable of quantum accuracy by design. And so one of the advantages of how quickly we can generate our parameter sets is that it makes these models highly conducive to iterative refinement framework, like I'm showing here. And so the idea is we can go through and generate some initial model. We can simulate with that model and periodically take configurations from that simulation, send it to our quantum-based reference method for data labeling, add it to our training set, generate a new model, and sort of iterate through this until we achieve our desired level of accuracy. And so here the idea is that our newer models are learning from the mistakes of their predecessors, where this helps us ensure our models are robust and accurate. And so this naive fitting framework actually works quite well for some of our simpler problems. But as we increase model complexity and the complexity of the chemistry that we're trying to describe, we need to use a few more tricks. And so to give you kind of a feel for what I mean when I talk about, changing complexity, what I'm showing here is kind of the chimes trajectory. So these efforts started out with an attempt to generate a model for molten carbon that worked at just a single state point. And so this was a relatively simple model, so only 2 and 3 body interactions, which gave us a total of 228 parameters that could be fit with less than a megabyte of training data. And so once we generated our training data, it took seconds to come up with our parameters. And so since then, we've been working on systematically more complex problems, which brings us to today, where we're trying to generate a transferable model for arbitrary organic molecular materials over the broad range of conditions relevant to energetic materials. And so now the models we're trying to develop have on the order of 10 to the 5th parameters and require more than a terabyte of training data. Where again, this is generated through quantum-based approaches that are very computationally expensive. And so this brings with it a couple of practical concerns. So for example, how can we accelerate generation and labeling of our training data? At the same time, how do we ensure it's meaningful and actually informative for our fitting purposes? And then perhaps a more subtle point is, what do we do if the systems that we're trying to describe have characteristic timescales that are inaccessible to our quantum mechanics-based reference method? And so to try to overcome these challenges, we've been using a few different approaches. So one of the things that we're doing now is using a multi-fidelity approach to model development. Where here the idea is this is going to allow us to make better use of existing data that might have been developed using different quantum approaches or let's say different levels of theory. And it's also going to help us accelerate our data generation. So for example, we can use approximate quantum methods that are faster than our reference approach to generate data for larger or longer timescales. We also use active learning as a way to ensure that the data that we're adding to our training sets are maximally informative. And so this is just sort of showing a schematic for one of the approaches we use to inform chemistry in our models. And then we also are using transfer learning to try to make these really large fitting problems a bit more manageable, essentially by recycling pieces of models we've already fit where possible. And so, as I mentioned, these model development efforts, or this whole CHIMES development effort, really was targeting description of organic molecular materials under extreme conditions. But what we found is that this approach is far more versatile than we had originally anticipated. And so this is just a selection of some of the applications we've looked at with these models, where this one here, here, and down here are talking about one of the newer directions that we're interested in going, which is leveraging these models as a rapidly parameterizable correction to some existing method. So in this case, we like to use this to tune approximate quantum methods like density functional tight binding. But perhaps more important is that this capability is really allowing us to foray into previously inaccessible problem spaces. And so, for example, we have this work that talks to shockwave-driven nanocarbon formation, and this work over here that speaks to sensitization in shock-compressed materials. And so for the remainder of this section, I want to talk in a bit more detail about this carbon condensation work to kind of give you a feel for the sorts of studies that this work has been enabling. And so before we do this, I want to start off with this question of, what is shockwave-driven nanocarbon condensation and why do we care about this? And so it turns out that we've known for the better part of a century that if you take a carbon-rich material that lacks sufficient oxygen to undergo complete combustion, like these materials here, so this is TNT and RDX, and we subject it to strong shock waves by, for example, detonating that material, we can form an array of interesting types of nanocarbon particulates. So here we have a nanodiamond, we have these graphitic nanoonions, and here we have agglomerates of these amorphous carbon particles. where these have a myriad of interesting applications spanning from drug delivery to quantum computing. And so there's a lot of interest in trying to turn this into a tunable process. But the problem is, in spite of the fact that we've known about this phenomenon for so long, we actually understand relatively little about how these particulates form, due in large part to the related conditions and the associated time and light scales. And so from the perspective of our experimental colleagues, these are very tiny things that form extremely rapidly. And so when they go and try to track their formation, their data seems to suggest that they instantaneously appear. And so obviously this is going to preclude extracting the associated mechanisms and kinetics. Somewhat ironically, from the standpoint of atomistic simulations, these are humongous particles that form over painfully long time and light scales, or timescales, particularly when you consider that this is a condensed phase reaction-driven process, which means we need quantum accurate models that are capable of simulation on very large scales. And so, of course, we became interested in seeing if we might be able to shed some light on this phenomena. And so in particular, we wanted to start by designing a reductionist study of this process to allow us to extract more fundamental but more broadly applicable insights into what's going on, and at the same time enable atomistic simulation studies of this phenomena. And so the system we decided to study was carbon monoxide for two reasons. So first, this is the simplest possible material that could undergo this phenomena, but also because there were experiments done back in the 80s that suggested that shock compression of cryogenic liquid carbon monoxide might indeed give rise to formation of these nanoparticles, though that hypothesis wasn't really investigated any further. And so we wanted to use chimes to see if first we could predict whether these condensates form, and if they did, if we can try to provide some insight into how. And so this work, of course, began with generation of a chimes model for carbon and oxygen systems under extreme conditions. And so what I'm showing here is just some of the validation data for this model. And so these top plots over here are speaking to recovery of system structure. So these are pair distribution functions. The black line is our chimes model. The orange line is going to be the quantum mechanics-based prediction. And the takeaway here is that we're seeing excellent agreement. Of course, we also care about chemistry. And so these two plots down here speak to that. First we have our concentrations and then corresponding lifetimes for the small molecular species that were found to form in the quantum and chimes simulations. And so the takeaway here is that we're seeing quantitative agreement with models that are orders of magnitude faster than quantum mechanics and can scale linearly with increasing system size. And so it turns out that this is important because when you run simulations at the quantum mechanics size limit, you see the following. So nothing. But using our chimes models, we were able to scale things up much further to over 1 million atoms. And when we did this, we saw the following. And so each one of these little red dots is an oxygen atom. And these black spheres that you see growing are liquid carbon droplets, so comprised of thousands of carbon atoms. And so what this simulation represents is the first time we've been able to use atomistic simulations to predict this condensed phase reaction-driven nanocarbon formation process. But perhaps more exciting than this is the fact that while we were developing this capability, our experimental colleagues were developing a first of its kind capability of their own that allowed them to probe the same system on the same timescales and overlapping length scales in a way that also allowed them to perform recovery. And so they performed their experiments, did their recovery, and performed TEM on the particulates that they found. And so this little Pegasus-looking creature over here is actually comprised of these smaller particulates outlined in these red semicircles that turn out to be the same size, shape, and chemical composition as what we predicted in our simulations. And so here we have this very compelling validation for our chimes models and this overall simulation capability, which then gave us the green light to go in and start to dig into the mechanisms and the chemistry and the kinetics driving formation of these nanoparticles. And so ultimately this allowed us to answer some decades-long questions surrounding formation of these materials. And so I'll wrap up this portion of the talk with just a few high-level remarks. So first, we're developing these tools enabling machine learning interatomic development for challenging energetic materials applications. But at the same time, these tools are also helping us foray into other sort of unrelated, previously inaccessible problem spaces. And so kind of overall, this work, this data science effort has been transforming our predictive modeling capability. And so in my remaining time, I want to just kind of switch gears and talk about some of the other work that we've been doing toward understanding material aging and performance, specifically in detonator or initiation systems. And so this portion of the work has been done with my other team shown over here. So let's start off with a bit of motivation. So stockpiled stewardship is one of the lab's most important missions. And among other things, this means ensuring that the detonators that we design and deploy in the field are going to work as expected. And so the key here is that detonators are the sort of system that you need for safety reasons to work 100% of the time. But the problem is that many of the materials that are in these systems can undergo significant changes in as little as 2 weeks if they are subjected to the right conditions. And so for this reason, we put a lot of effort into trying to design robust detonators that are going to function as expected over their potentially decades-long lifetime, while in tandem developing diagnostic tools that can be used to check up on their health during that lifetime. And so we do this through what we call our MAC and P cycle for materials aging, compatibility, and performance, where the idea is shown here. So we're going to start off with some initial set of engineering designs for a detonator. And so using these designs, we are going to manufacture tens to hundreds of these detonators, all of their various different components and the materials that go into them. And then we're going to take them and subject them to a comprehensive characterization. So this can be spectroscopy, imaging, X-ray computed tomography, so forth and so on, where our goal here is to establish sort of a baseline health report for all of these different components. And so once we do this, we're going to take all of these samples and subject them to accelerated aging experiments. So this will be, for example, at elevated temperatures or humidities, where I just want to note that these accelerated aging experiments can last for years, so they're not as fast as you might think. And so at the end of these aging experiments, we're going to take all of our components, recharacterize them, and then function them. And so now what we're looking for are changes in their performance that are outside the margins permissible in the original engineering design. And so if we see something that looks anomalous, we have to sift through all of this characterization data, try to figure out what went wrong, address it in a new design for the part, and iterate through this cycle until we achieve our desired level of sort of robustness. And so traditionally, this inspection of our characterization data has been done by subject matter experts by hand, and this has a few disadvantages. Of course, this is going to require significant human resources, but more importantly, as humans, we are very unlikely to be picking out all of the information that this data has to tell us. And so for the rest of this talk, what I want to address is how we've been starting to use data science to try to expedite analysis of all of this data, extract more from our data sets, and develop better age-aware diagnostic models for performance of these systems. But before we get into that, I want to just give a little overview of detonator anatomy and how these things work. So what I'm showing here is a vertical cross-section of what's called an exploding foil initiator type detonator. And so what we see here on the bottom is a substrate upon which we have a metal foil layer. And then on top of this metal foil, we're going to have a polymer layer. Sitting on top of the polymer, we have a ring-shaped barrel. So remember, this is a cross-section. And then on top of our barrel, we have We have an explosive pellet that has a little metal hat on it. And so this white region in here is a gap between our polymer surface and the explosive pellet. And so this type of detonator is functioned by dumping voltage into our metal bridge, which is going to cause it to vaporize and form an expanding plasma. And so this plasma is going to stretch our polymer until it eventually tears away and forms a flyer. And so you can see an image of this where this is rotated now 90 degrees. So you can see the flyer that's formed, we've ruptured and pulled away from the rest of the flyer, or the polymer material on the substrate. And then you can see the shape of this as it moves further away from that surface. And so this flyer is going to travel across this air gap and smack into the bottom of our explosive pellet, where if the energy delivery is sufficient, it will detonate that explosive, and that would represent a successful functioning. Okay, so as you might imagine, age-induced changes to the structure and the chemistry of all the different components in these systems can have a significant impact on their performance. So for example, we might have microstructural changes on the surface of this pellet that could potentially rupture our flyer. Or perhaps there are changes that cause a density gradient across this material that could impact our energy delivery. And so the question becomes, well, what sort of characterization data might we look to inform these changes? Now, as I had mentioned, we do perform quite a bit of different types of characterization, but for the sake of today's presentation, I want to focus on what surface profilometry. And so the idea with this characterization technique is it's going to tell us what the heights across the surface of our pellet look like. And so this is just an image of this profilometry data for a pre-age pellet in the back and then a post-age pellet in the front. And so you can see things like inherent microstructural features, these little blobs you can see all over the place. We can also see things like scratches, so this guy over here, dust, etc. But we can also see age-induced changes in these materials. So if you look carefully, there's lots of little red dots all over the surface that represent formation of pits in this material. So that might have some sort of impact on our device function. So we know what these detonators look like. We know what sort of characterization data we might consider. So the last piece of the puzzle here is what sort of performance metrics might we care about. And so for today's presentation, I want to focus on threshold voltage, which essentially is the voltage at which we expect a 50% likelihood of either a go or a no-go event. And so with all of these pieces, we can start thinking about building diagnostic models. And so to do this, we need to first select a functional form. So for today, let's focus on this relatively simple, just linear fit. So we're saying our threshold voltage, we believe, is some weighted sum of a feature. So this can be based off our characterization data times a weight. And so to define these features, we can use, for example, industry standard representations of our profilometry data. For example, the root mean square error or deviation in the heights of the surface, or the skewness of the distribution of heights, so forth and so on. And so given that and our performance data, we can try to train these diagnostic models. So let's see how this works. So this is a model that was developed to predict performance for samples that had 2 different explosive pellet densities and were subjected to 3 different aging conditions. And so each one of these data points is going to represent one of those sort of classes of density and aging condition. And so on the x-axis, we have our experimentally predicted threshold voltage, and on the y-axis, we have what our model predicts. And to put it succinctly, this performance is terrible. So what's going on? Is it a problem with the underlying model? Or is it the fact that profilometry isn't probing the actual microstructural or chemical changes that dictate performance in this material? Or is it the fact that these industry standard features that we're extracting from this profilometry data are not capturing the sort of key changes in it? And so to try to probe this latter question of whether featurization is the problem, we decided to try to reanalyze this data using computer vision. And so the approach that we're using is based off this idea of bag of visual words. And so this set of pictures over here kind of explains how this works. So we'll start off with some collection of images from which we're going to try to learn a visual vocabulary, which is shown down here. So we have these visual words that describe an eye and a cheek and a bicycle seat and the bass of a violin. And so now using this vocabulary, we can try to describe the images that we feed into this framework. And so, for example, the picture of the woman might now be described through a frequency histogram in these visual words that is peaked in the cheek and the eye feature. Similarly, a bicycle might be peaked in the bicycle seat picture, and so on. And so for our data, this now looks something like the following. So the pictures that we are trying to learn microstructural features from look more similar to this. So this is another profilometry image, just this time in grayscale. And when we process a bunch of these, we're going to come up with, in this case, 50 features to describe them. And so one of the things I want to make clear here is that each one of these can be tied back to a physical attribute in these materials. And so now that we have these features, we can start building diagnostic models that try to predict performance based off of these features. And so down at the bottom, we have our previous very bad model that's trying to predict performance based on our industry standard features. And then over on this side, we have a model that is using the same profilometry data, but this time using features that come from our computer vision approach, where now you can see that we're actually getting good agreement with the experimental predictions. And so ultimately, this approach is helping us extract more information from the data that we already have. But we can take this a little bit further. So for example, these models are trained using lasso regression, which if you have a careful eye, you may have seen in the earlier slide. It's one of my favorite techniques. And so one of the things that this does for us is it's going to automatically try to determine which features are most important to the fit and throw out the ones that don't matter. And so we can take advantage of this approach to, for example, generate strongly regularized models that look at performance in only our high density pellets. And when we did this, we found that only 3 words were needed to generate accurate predictions for the performance of these samples. And so now we can go back to our visual vocabulary and look up which microstructural words correspond to these points. And so from this, we were able to learn that in these high density samples, these words that were picked out by your model correspond to pitting in the material. And so now we're learning something about what physical attributes govern performance in these aged materials. Or worded otherwise, we're learning the language of material aging and performance. And so I'll wrap my talk up here with a few more high-level remarks to leave some time for questions. So first, data science is really improving how we analyze what relatively we believe are our large data sets and helping us make heads or tails of these disparate experimental data sets that we get. So lots of different types of characterization data, lots of different types of detonators and materials, so forth and so on. These tools ultimately are allowing us to extract more from our data, streamline our experiments, and develop high-fidelity diagnostic models. And so holistically, all of these sort of data science endeavors that my teams are working on is really transforming our predictive modeling capability. So I'll end my talk there and would be more than happy to answer any questions.
Thank you. That was lovely. Let's see. Anybody else but me? I'm reading one, but people, by all means, you're well. Oh, you cannot. I have to read them. Okay. What optimization method are you currently using to solve the distributed lasso problem, and at what scale? Yeah, at what scale I was also thinking. Please.
Right. So our lasso solver is currently working quite well for on the order of tens of thousands of parameters. But when we get much beyond that, it's still, we run into just resource issues. So it will distribute, but the question is it efficient in the sense that, we'll need to request hundreds of nodes to solve those problems. And so I'm sorry, what was the first half of the question?
What optimization method are you using to solve the distributed lasso? That's the first. And the second was at what scale? I think you answered what scale when you said 10,000, but I was wondering more. I don't know if that's what the person who asked the question meant. what scale of features, like if you look at the simulation and you try to pick up words from the simulations you have already done, what would be the group of words that you would use to then discover the language? I don't know if I was, the first question is, what do you use to solve the lasso? And the second was, at what scale?
So we're using LARS to solve the lasso equations.
Okay.
And for the scale, I don't know that I fully am understanding what this.
In the pictures that you said, there was the subscale that was cheek or eye or whatever. But if you have to choose the words based on your big anthology of simulations that you would have done, if you were going to adapt your dictionary to things that you have produced, what size of a simulation, what window would it be?
I see. So the visual words work is entirely based off of experimental data sets.
Of course.
So in that case, the scale, well,
you had a picture that showed 4 pits, right? So it would, if I saw it correctly. So when you said pitting, no, in the next slide, when you said that there was something where you said we recognize that in the aging, it is pitting.
I see. So, right. So each one of these features, this is like this feature that we see here would be roughly the size of this little white dot that we see here. So I don't know if you can see it on your
pointer, so I don't know.
So
are you talking about one of the little red squares on the little red squares? And now I see your pointer. Yes.
Right. So this
guy, yes.
This square here, this is a word, a microstructural word,
Yes.
which when we try to relate this back to our image is going to be on the order of this little white dot that you see over here.
Okay.
Now, when we go through and try to define these words, there are far more than the 50 that we're showing here that might show up. And so basically the idea is we're using this SIFT method to try to pick out candidate words. And then we're going to try to cluster these words into some representative, cluster. And so visual words that seem to be very similar will be assigned the same sort of cluster, and that cluster becomes the word that we have here. And so, for example, you can use like k-means or whatever to try to set a specific vocabulary size.
So in like, there's 2 minutes until the next talk. Maybe I can ask, what is, at what level does somebody go in and say, aha, this picture is pitting?
Well, originally, that's kind of how all of this work was done. Someone would just stare at these images and say, I see lots of pitting, that might be a problem. So for us, there's 2 members of our team. We have the feature extraction members of the team, and then we have our model development members. And so the feature extraction members are going to try to do this kind of without injecting subject matter expertise. And so one of our sort of sanity checks is, okay, when we go through and process the features that our model tells us are important, does this make scientific sense? And so that also tells us that our feature extraction approach is working well.
Okay. I mean, a thought. I think in what there is a statistician at the University of Washington called Marina Meila. You may know her or run into her. One of her works says, here is a bunch of features that I've found. Here is a bunch of possible candidate words that somebody gave me. We've also done some of that. Can we check one-to-oneness of these things on our data, which is one way of trying to. So it's not that this is pitting, but it's one-to-one with pitting. So it's as if it was pitting.
Right. So that we're exploring something kind of similar to that. So 2 things. First, transfer learning, trying to apply this accelerated aging vocabulary to actual field age samples and seeing if it works the same. But also we can use the same approach on data that's generated through, for example, continuum simulations. And we can actually manufacture these sorts of structures and see again if they actually map to what we think.
Thank you very much. It's still 1:55, so we are good. I appreciate the talk. Lovely. Next.
Thank you.
Wonderful. Good afternoon. My name is Charles Meneveau. I serve as IDIES Associate Director, and I also wanted to join in thanking Dr. Lindsey for a wonderful talk. Very interesting, all this so many scales and so much complexity and still making sense out of things. So wonderful. And now, of course, it's my pleasure to introduce the next speaker, Dr. Thomas Lippincott. Tom, you're there. Okay, good. I can see you. Very good. So Dr. Lippincott is a awardee of one of the IDEAS Seeds Awards. And let me tell you a little bit about him. So Tom is an assistant research professor of computer science affiliated with the Center of Language and Speech Processing and research scientists in the Human Language Technology Center of Excellence, with secondary appointment in the Alexander Grass Humanities Institute. He performs research on how machine learning can support and facilitate traditional scholarship in the humanities. He has a bachelor's degree in philosophy and computer science from Chicago, and a PhD in computational linguistics from Cambridge University. And today he's going to talk about unsupervised neural framework for multimodal literary and historical scholarship. Fascinating. Tom, the floor is yours.
Thank you. Can you hear me all right?
Yes, and we can see
Wonderful.
the slides.
All right. So thank you for that introduction. My affiliations have actually kind of flipped in polarity here. I am now a assistant research professor in the Krieger School of Humanities with a secondary appointment in computer science. But I'll get to that in a moment. So I'm going to be talking about this research that we're undertaking right now, realizing an unsupervised neural framework for multimodal data sets that are being drawn from literary and historical scholarship. And the way that this was proposed was really a collection of potential practical tasks that surround facilitating this kind of ecosystem that will allow us to kind of uniformly develop and apply these models. And so this ecosystem has a few axes to it. And of course, we're never going to be able to cover all these axes in a year. So there was a wide range of possible ways this research could go, or this grant could go. But the axes that we were considering were first a kind of stable representation that could be used in a wide variety of different humanistic research endeavors. And we've pretty much settled on a dialect of RDF, Jason LD, which is familiar to both our target audience, which is these traditional scholars, but is, of course, RDF is a kind of the gorilla in the room when it comes to semantic representations and structured representations, and a lot of very cool stuff that you can do on top of those layers, like inference rules and so forth. We need to have some sort of mechanism for scholars to both annotate and structure their primary sources in kind of field-specific or even domain-specific ways, but also be able to add layers of annotation of their own to it, kind of scholarly knowledge that is linked into it. Of course, this is all centered around this idea that we're going to be able to use that structure to tie things in with tie things into the current state-of-the-art of deep learning. Where we have lots of work on multimodal, structure-aware models, pre-training, and so forth. We want to be able to do that in a principled way. And of course, we also want to take advantage of this structure, however it pans out, to also do a lot of public humanities. We want to be able to have the humanistic scholars that we collaborate with have some very tangible takeaways from this that they can point to and that will help their career. So something like interactive visualizations and automatically generating web pages and websites and entire interfaces based on the structure that is now kind of reified in these graphs and the output that is tied to it from these models. So that's a lot of space. Now, there was also an unanticipated development that happened about a month after we started working on this project, which is that I was asked to start the Center for Digital Humanities over in Krieger. Now, this is a complication, but a very welcome one, because we now have a dedicated place to put a lot of this. And so we now have this cdh.jhu.edu site that is slowly coming online, and will host a lot of these things and make it easy for people to find and interact with. So a lot of this was centered, or a major component of this research is centered on this idea that we have a couple of paradigmatic research collaborations that are going to help us choose which which axes and to pursue most strongly, and how to fill them out in a way that is going to help a lot of downstream research. So let me just quickly describe those two research studies. So the first is centered on this corpus called the Early English Books Online, which contains English language publications spanning basically from the start of modern English, pushing back into the 1500s, early 1500s, up until I believe about 1700. It consists of about 60,000 published documents. We kind of iterated over this with a number of graduate students and professors from the English department about what kind of questions we wanted to focus on. And we focused on, we narrowed it down to this question of how did British attitudes towards Ireland shift over time? Okay, so this is also nice because it's it lines up nicely with my background in natural language processing. The other study from a completely different department in Krieger is with the Near Eastern Studies Department, who are very interested in what's called the Cuneiform Data Library Initiative, which is the world's largest collection of cuneiform inscriptions. And this consists of about 300,000 inscriptions from the 4th to 1st millennium BC. The metadata for this is very rich and also rather messy, but it comes with images, it comes with transcriptions, it comes with line art that has been produced by kind of like hand drawing reproductions, like lithograph type stuff that has been produced since the very beginning of the field. And we've narrowed down on this question of how do a bunch of these properties vary with respect to an existing scholarly hypothesis that claimed that they were able to identify scholarly hands in a particular subset of this material. So the idea is that in ancient times, there were very few people who were actually literate to the point of being able to produce these. And so there were a number of scribal centers, and it's unclear where letters exactly came from, who actually wrote them physically, but we suspect that we're able to get back at that information looking at properties of the text. And I'm afraid that I only caught the very end of Rebecca's presentation, but I suspect that there's a lot of interesting overlap here, because I think that it seems clear that a lot of the signal for the sort of authorship or sort of domain provenance of these artifacts is going to amount to things like microscopic or beyond human perception properties of the material and the handwriting and so forth. And so I'm very interested in the visual side of things as far as that goes. So we've done a little bit of, we're really just ramping things up at this stage, but we've done a little bit of work on some unsupervised topic modeling as applied for this question of the British attitude towards the Ireland, which amounts to Irish rebelliousness. That's usually how it was characterized. And here are some of the topics that we were able to that came back to us when we ran topic modeling. You can see that there are some interesting things in here that I won't go into and unpack in depth, but there are correlations between particular individuals that we're able to identify and their particularly, I guess you would call it bloodthirstiness, the sort of violent relationship they had with Ireland. Questions about Catholicism versus Protestantism, questions about land ownership and tenancy and rent and that sort of thing. These are all very important topics. And this snapshot that we have right here, I think is going to yield some very fascinating diachronic results when we turn the topic model around and look at how these things have varied individually and in tandem over time, because at least the ground truth, or not the ground truth, but the initial hypothesis here from the domain-specific scholars in the English department is that England shifted from having a rather antagonistic relationship that was purely exploitative in the early times to becoming more and more paternalistic and kind of at least ethically sounding in their approach to how to deal with the particular problems presented by the protectorship of Ireland. So I mentioned that we've settled on this RDF data format. This is just an example of what this sort of looks like for a little fragment of data that you might want to put into RDF, and it can all be expressed using this JSON format. And the interesting thing here is that it's multimodal. Well, one of the interesting things is that it's multimodal. So we have images that are embedded in it. We have links to Wikidata entries to try to prevent redundancy in the way that things are represented across studies and even across fields. So it would be very nice to, for example, know that an author that is in a data set that the English department is interested in is the same entity that occurs in, say, an economic study of slave ownership that's being done by the history department. It would be nice to be able to share that information and even have models sharing parameters based on that linkage. I mentioned annotation as being very important. So we have an existing tool that has been developed at Johns Hopkins called Turkle. This is a feature parody clone of Amazon Mechanical Turk, which is the very popular crowdsourcing tool. Or framework. And we've been working on some extensions to that that will facilitate more focused types of annotation. Because if you are familiar with Mechanical Turk, you write these templates that can that essentially generate HTML and JavaScript, perhaps, that is useful for the particular annotation task you have in mind. And then there's kind of a library of built up techniques for tasks that show up quite a bit. We want to have a nice suite of those available for our collaborators in the humanities to be able to use and maybe slightly adapt. So in this case, we're looking at the interface that was developed for a project that was looking at Chaucer's scansion. So this is the metrical qualities of his poetry. And this tool, or this, I should say, this particular instantiation of a Turkle template does a lot of the work for the scholar in terms of ensuring consistency and presenting coherent alternatives in terms of the metrical qualities, but also the grammatical tags that are on the words. And so scholars can quickly iterate over this and correct the data or add annotations to the data. The second image here is of this is an internet image, so I don't claim this is anything directly coming from our research. But this is the basic idea is that we would like to have a nice drop-in vision image annotation framework that uses IIIF format as the kind of language of communication and will allow scholars to get past this longstanding bottleneck of having images that are, say, poorly OCR'd or not being able to directly annotate images and having to only tabulate their information in scholarly publications using standoff, just kind of free-form text right next to the image, which is not a very good way to create structured scholarship. And then we're looking at a number of ways of extracting information both from new types of models and from existing models, like the topic models that I showed earlier. So we're looking at some tools like the linguistic inquiry by word count, and we're looking at ways that these extracted signals vary both diachronically but also geographically. So there's been a fair amount of work on diachronic word embeddings, yes, word embeddings and topic modeling. But moving that beyond to, say, 3 or 4 dimensions so that we actually have both time and geography as well, and then creating appropriate visualizations for those that could produce some very nice public scholarship and interfaces for people to present their research with. And I won't go into this too deeply. This is the StarCoder unsupervised graph-based autoencoding model that kind of generated the ideas, or a lot of the ideas around this research. And a lot of the tasks that I've described up to this point are ways of supporting this model and its output so its input and its output, in a way that will make it more seamless for humanists to be able to bring their own data and then take away the output and interpret it in a kind of more intuitive way than is typically the case when looking at machine learning model output. And finally, just looking further ahead, we're going to continue analyzing and visualizing these results with the scholars. A broad organizing force behind all of this is that we really want to democratize the access to all of these methods. So a lot of interaction with Krieger School and trying to bend all of these tasks in the direction of being more accessible, even at the simple graduate student level. And then generating copious amounts of documentation and pedagogical material so that we're able to quickly introduce people to it. All right, thank you very much.
Thanks very much, Tom. Very interesting. All right, so the floor is open for questions. I'm going to monitor the chats here. Maybe as I look if there are any questions, I had a quick question. I was struck by this idea that you'll have essentially, a lot of diverse people making these annotations, and I wonder whether, how uniform that can be, or how, whether that's a problem to have, the annotation being done by many different people. Where I think, other than different from the exact sciences, it's probably much more challenging to end up with kind of uniform criteria.
It's certainly very challenging. I mean, I think that there's a fair amount of that already in linguistics and NLP, although this is another order of magnitude on top of that, I think. A lot of these tasks are very much engineering goals, where we're trying to find the sweet spot between over specialization and kind of too much generality, where we're able to kind of pivot very quickly and make things accessible to individuals and broad swaths of individuals on short notice. So that's definitely a negotiation that is a big part of this.
Yeah, thank you. Let's see if there's any. I don't see any questions. Maybe one other question. I was curious. What do you see as the sort of the major challenges to educate the humanities people to use these sorts of tools? Is there resistance to it? Is it straightforward? How does that work?
Right. So at this stage, I'd say that there's a lot of self-selective participation. So of course, it's very good experiences with the people who are showing up and really want to be involved, and that is already kind of maxing out my energies and time. But definitely for scaling it up, I think that there's a very good argument to be made, and whether it will ever be successful is a different question. But there's a very good argument to be made that there should be some module in graduate education that introduces at least some of these things, and not the specifics of what I've laid out here necessarily, but kind of the broad advantages and disadvantages of computational approaches to humanistic questions, because I think that people should at least know what they're rejecting before they reject it. And I think that's very feasible, and there is I've got positive feedback on that. So
okay. Wonderful. Okay, so we wish you, of course, good luck with the seed project, and parlaying that to other activities and future growth. So wonderful. Thank you again.
Thank you.
All right. So I think we're right on time. So it's 2:15. So the next presentation that I'm delighted to introduce is by Dr. Jaime Combariza. Jaime is Associate Research Professor in the Department of Chemistry, and he's really the director of what used to be MARCI, the Maryland Advanced Research Computing Center, which is now ARCH, and he will of course tell us about the evolution and the changes. He also serves on the IDEIES Executive Committee, and he's going to give us an update. But before I leave the floor to him, I really wanted to take this opportunity to reminisce about the past at Hopkins in terms of high performance computing. Maybe he doesn't know this, but as little as 10 years ago, Hopkins, at least in my field, we were considered okay in theory and experiments, but this was a computational desert. We always felt underserved. There was nothing going on in computing at Hopkins. It really was sort of really on the low end of things compared to other institutions. We always felt sort of little. Fast forward now, Hopkins is in a very strong position. Rockfish is a node in the National Seed Supercomputing Network, et cetera, et cetera. So it's really remarkable to see this turnaround, and quite a bit of it is in large part due to Dr. Combariza's efforts. So he will now tell us about more recent developments that have taken place. So Jaime, the floor is yours.
Thank you. Thank you very much for your words, Charles. Can you all see my slides?
Not yet. Not yet.
Okay, now we're having problems again. Oh, I need to share my screen, right?
Yes, that you have to do.
That I should do.
Yes, it's moving now. Okay, yep.
I'm sorry about that.
Very
All
good.
right, good. So I'm going to give you an update on the status of high-performance computing at Hopkins today. And Charles is absolutely right. Today we have a very powerful instrument. And that is based on a couple of grants that we got from the National Science Foundation and the Department of Defense, and also contributions from Johns Hopkins, in particular, Krieger and Whiting. As Charles mentioned, this is a collaboration with EXCEED, the national facility, and also with Morgan State University. This is the way to contact us. As Charles mentioned, we have a new name. So this is our new website, www.arch.jhu.edu. And the way to contact us for questions or comments or whatever is help@rockfish.jhu.edu. So before I do some presentation, let me say a few words about advanced scientific computing as is seen by some of the funding agencies. So we all know that science and computational research are continuously evolving, as the first talk showed today, and often at a very fast pace. So for us, this means that, first of all, we have access to more powerful systems like Rockfish. That means that, again, as mentioned in the first talk, the simulations and the modeling is now different. It's optimized, it's improved, it's much better. We are able to do higher accuracy, high fidelity, and that we can also include experimental or observational data and machine learning. We have advanced or very sophisticated software packages optimized for new hardware. And we have many tools from AI and ML that are open to anyone. And this is basically the result to accelerate discovery and innovation. But now the question that we have is, how does scientific computing support fit into all this ever-changing environment? And this has a very impact on what's called now team science, the interaction between the researchers and the support people. And the skills and the expertise of these people are in high demand and badly needed to optimize workflows, to install applications, and to help work with users so they can effectively use these applications. We aim at optimizing utilization and basically minimizing wasting of resources, which affects everybody. So the challenges for the workforce are high. Not only on the technology side, because new technology is available every year, but also the new skills that people have to acquire and polish to be able to work with everybody, in particular with artificial intelligence. So we have two systems today. Last year I mentioned that the Blue Card is going to be decommissioned by June 2022. We wanted to do it early because it's failing quite a bit. But because of the problems with supply chain, we have to wait a little bit longer. So still June of 2022. But the Rockfish has been available since April of this year. So it's about 6 to 7 months in production. We started with over 18,000 cores. By January of 2022, we're going to have 35,000 cores. That's 50% more than the Blue Crab. And we have only room to improve. We have 16 petabytes of parallel file system, so plenty of space for your data-intensive computing. Well, we provide, this is a duplicate from last year, but basically all the cycles, all the resources that you need to do your number crunching, data intensive, machine learning, singularity containers if your application needs on a special environment. We also provide interactive access for Jupyter Notebooks, Jupyter Lab, RStudio, and so forth. We have very fast data transfer to Globus. And we have hundreds of applications installed, and more importantly, probably scientific support. For Rockfish, we're using a portal, so we allow PIs to manage their allocations and their users. This is the URL for the CallFront, the portal. It's called callfront.rockfish.ehu.edu. And as I mentioned before, our website is a new website. And basically, this portal has three components. So the first part is for PIs to request allocations and create projects to be more than one. When we have a link for users to request accounts, and then the PI or the proxy should be able to add those accounts to the project. And finally, a link for people that need to reset password because they forgot or whatever. This is a picture of our new website. There is already plenty of information in here. And there is more that is coming. There is information about policies, which is very important for everybody, how to access the system. But I'm going to point out the user guide, which is a very detailed description of how to use the facility, how to connect the type of queues and so forth. So we also have a lot of PDF files and videos on the website that is going to help people to navigate to the system. A few words about the business model. So again, I mentioned this last year. For an instrument of this size and capability, the cost is going to be between $8 to $10 million. We cannot expect that a single institution is going to provide the funding for that. That is, the university is not going to be able to do that. That is, funding agencies won't be able to do that. And that is much less the PIs by themselves providing all the compute power. So we propose this three-leg model based on a group of large grants, NSF and DoD, which we already got, and then a medium grants like the schools that are going to provide condos, and then small grants from different research groups. Is this model working? Well, today we have 462 nodes from the large grants. That is 60% of the facility. And that also includes a common infrastructure for the other condos. We have 126 for the dean's leg and 150 from 25 individual PIs. So I believe that this model is working, and there is also room to improve because I know that there are several other people that are going to add condos in the near future. So this is a very powerful facility. As Charles mentioned, at the academic level, it's a very, very powerful instrument that should be used very heavily for your research. A few words about the community condo model, because I've been asked a bit. All the resources are shared, meaning that if anybody buys a condo, nobody has access to dedicated resources. And the trade-off is that if you share your condo, you don't have to pay for the system administration, and that's a big plus. And you allow other people to use your resources when you're not using them, and you should be able to also use more resources if you need it within your allocation. Anybody who has a condo is going to have an additional allocation according to the number of hours that condo produces. They will have higher priority. So there is no way to complain that I'm waiting too long in the queue. But more importantly, it will contribute to the sustainability of the system, which is very important for the future. I mentioned the workforce development. We provide training almost every month, different sessions, because we believe that it's important for the new users and existing users to find out how they are using the resources and to minimize waste. Redundancy, if you remember, we had a big problem in the summer, the chiller, the cooling problem. So we are adding resiliency. We're adding another chiller for backup. So hopefully next summer, we're not gonna have those problems, or we're gonna minimize those problems. We have data backup. We are gonna have a dual platform networking. And we're working on a contingency plan in case of an outage, an extended outage, so people don't have to stop computing. They may have to reduce their computing, but they will still be able to access the facility. Again, our best way to contact us is through our website or through our help system, and I'll be happy to answer any questions.
Thank you very much, Jaime. Thank you very much. Are there any questions? Looking at the chat, looks like everything was very clear, Jaime. You're providing a lot of useful information, so thank you again. I believe we now have a 10 or maybe a little less, 6-7 minute break till 2:35. So we go on the break now. Thank you.
Yeah, so welcome back to the session. And our next speaker is Dr. Ryan Abernathey. And Dr. Abernathey is a physical oceanographer who studies large-scale ocean circulation and its relationship with the Earth's climate. He received his PhD from MIT in 2012 and did a postdoc at the Scripps Institution of Oceanography. He has received numerous awards, namely the Alfred B. Sloan Research Fellowship in Ocean Sciences and NSF Career Awards, the Oceanography Society Early Career Award, and the AGU Falkenberg Award. And he's a member of the NASA Surface Water and Ocean Topography Science Team and the Director of Data and Computing for a new NSF Science and Technology Center called Learning the Earth with Artificial Intelligence and Physics, and the acronym is LEAP. Dr. Abernathey is an active participant in and advocate for open source software, open data, and reproducible science. And I would like to add a personal note. So over the last 2 years, I learned an enormous amount from Ryan in how our future computational systems in science will look like. And he's going to share his experiences with us. Welcome, Ryan.
Great. Thanks a lot, Alex. Thanks for the invitation, and thanks to the organizers for inviting me. This has been a really interesting meeting so far. So I'm going to talk about my vision for cloud native science. I think Alex's introduction was fully complete, so I'll just skip over my introduction slide. But there's a lot of new faces here, people I'd love to get to know, so feel free to contact me offline if you want to follow up about anything. So the plan for my talk here is to I'm going to try to define what I mean by cloud native science and why this is the direction I think we should be heading in. I'm going to give a little demo of Pangeo, which is sort of our platform for cloud native science. I'll talk a little bit about how this technology works and what I think are some of the reproducible and reusable elements of it. And then I'm going to talk about what I see as the big challenges for cloud native science going forward. In case you just happen to fall asleep, it's that time of day, post lunch when attention wanes. Most everything I'm going to say is written down in these 2 papers. You can follow up there also for more information. Okay, so the motivation for this work is, I think, something most people here are familiar with. We're in a real golden age for scientific data. The sensors that we have to collect data, I'm an oceanographer, so I'm speaking about the Earth, but the sensors we have to collect data are getting more powerful every day. New platforms, new instruments, the simulations we can run to understand our natural systems are generating more and more interesting, fascinating data. It's really such an exciting time to be doing science and data-intensive science in particular. The flip side here is that we have a huge challenge related to the volume of data that we want to look at. So here's a graph from NASA about their Earth data holdings, projecting that within just a few years they'll be holding 200 petabytes of Earth science data, which is a very intimidating number. And it's not just in Earth science where this is happening. The astronomers are probably very keenly following the progress of the James Webb Space Telescope, which will undoubtedly be dumping ungodly amounts of beautiful data upon your field very soon. I'm moving downscale a little bit in terms of microscopy, genomics, new technologies like light sheet fluorescence microscopes are imaging cells and biological systems with amazing fidelity and detail, but they, again, we get into this problem of petabytes and petabytes of data that we want to work with. Now, what do people want to do with all this data? I think it's important to remember that a lot of applications, a lot of really high impact science can be done through simple statistical analysis of very large data sets. So for example, NASA is collecting a lot of high, detailed sea surface height measurements. We just take the mean of those. What we see from that is this sort of inexorable global sea level rise. that is a a smoking gun footprint of global warming. Of course, we want to understand the patterns of spatial temporal variability in all of these data sets. And of course, being 2021, no one can even consider not doing machine learning on all of this fantastic data, right? So there's so many exciting new methodologies that can be applied to extract new insights and learn about physics and discover patterns. And what these workflows all have in common is that they require you to really work with the whole data set. You're not just interested in some little piece or some little subset. You want to process the whole data set or a large data set to train your model or to calculate the correct statistics. So, here we get to this reality that across data science and including, scientific data science, a huge amount of scientists' time is really spent downloading, cleaning, and organizing data rather than doing the more perhaps glamorous work of actually developing algorithms or models. This was recently highlighted in a paper by some AI researchers at Google entitled "Everyone Wants to Do the Model Work, Not the Data Work." And these authors really emphasize that the goal of incentivizing data excellence as a first-class citizen of AI. So all these great methods, all these great new tools that we're getting from AI and ML, they're really not valuable unless they're paired with high-quality data and accessible data. So if you're like me, you grew up with this idea that the way we work with data is we download it. We download files to our laptop or our local computer, and then we analyze them there. And that works just fine when we're measuring our data size in megabytes or even gigabytes. Once you get to terabytes, this way of working gets pretty painful. And at petabytes, it's essentially impossible. Now, the solution to the way around this, I think, of course, many of you already are well aware of, and the Johns Hopkins Sci-Server group has really pioneered this idea of data proximate computing. Rather than bringing the data to your computer, you go to the data and do computing there. So I consider that a version of cloud computing. I think that the definition of the cloud is somewhat ambiguous. But when we have both data and computing in the cloud, right now we have very powerful approach to doing data intensive science. We have interactive computing that we can do through our browser using Jupyter and all of these great open source languages, Python, Julia, and R. There are parallel computing frameworks like Spark or DAS that we can use to scale out our processing. And then over on the data side, we have all these great new analysis-ready data formats for cloud-optimized data. And so this is really the vision for what I mean by cloud-native computing, where rather than downloading the data, we bring our computing to the data and use these type of frameworks and technologies to do science. Now, this type of scenario can be realized in many different architectures. It's not just in AWS, right? This sort of thing has already been happening for years within the Sci-Server environment. We can do this on an HPC machine, but it does work particularly well in the commercial cloud for reasons that I'll get into. So why should we be moving in this direction? Well, we tried to articulate this in our recent paper, and we really identified 8 main benefits to trying to work in this cloud native way. And I'll highlight a few of them. Performance. A huge benefit that we get from doing our data work in the cloud is elastic scaling. We can very quickly scale up and down an analysis using a whole bunch of computing for a very short time. And that can really make our progress a lot faster. And that can be harder to do in a traditional HPC environment where there's a finite size resource and a queue to wait in. Another big aspect is reproducibility and collaboration. If we're all using a common environment, if I can really easily bring new collaborators into a project, share my code with others and have it actually work, share data and let other people access the data in the same computing environment as me. Another really exciting thing about the cloud, particularly in earth and environmental sciences, is that there's this whole downstream ecosystem of industry partners who want to work with the same data. A bunch of new companies, such as the ones listed on my screen, who are really partners and are consumers of this data. And so by having our science happen in the cloud, we build these links to industry that can be really strong and have really, really great outcomes. And a final one is just the accessibility of cloud computing creates a lot of new potential for access and expanding access, participation, and inclusion. So for example, in Pangeo, this summer, we partnered with the Coastal Ocean Environment Summer School in Ghana, providing a cloud computing environment for these scientists to work in, where they could access huge ocean data sets over a small internet connection. And therefore, they became sort of unconstrained by their local computing infrastructure. And I think that's a really exciting dimension to this. So the pillars I see for cloud native computing, cloud native science, are this combination of analysis ready, cloud optimized data, data proximate computing frameworks, and then scalable on-demand distributed processing. So right now I'm going to switch over to a little demo. This is a demo that you can reproduce yourself on demand by following these URLs, including this tiny URL link. Unfortunately, I have to take this off the screen now, so maybe someone managed to catch that. Otherwise, you can just follow along. So when I go to this page, I will get a link here for a Jupyter notebook. It's a static version of a data analysis workflow. And if you click on this launch binder button, it'll open up a new interactive environment where you can run that yourself. I have one already started up over here that I'm just going to run for you and walk through some of these steps in this notebook. So what I've done in this cell here is I've just, from our data catalog, opened up a giant data set. This is an example of analysis ready cloud optimized data. Here we have got variables like sea level anomaly, hundreds of gigabytes stored in a chunked compressed format in cloud object storage that I can open with 1 or 2 lines of code and access all of this rich data and metadata. From that, I can, I have to do my imports here, sorry about that. From that, I can create a interactive visualization. So I can plot this data on demand and stream the data directly into my notebook without really downloading it, just because I'm right next to it in the same cloud region. This is happens to be running in Google Cloud, so I can sort of scrub through this sea level data and explore the data set interactively. And then when it comes time to process a lot of data, I can use parallel distributed computing. So in this cell over here, I'm just going to compute the time series of mean sea level anomaly through this cluster. And I'll open this dashboard up so we can see what's happening here. So what's going on here is that I have started up this cluster. It is, for some reason, zooming in on the region where I do not want to be, where we are now using about 20 compute nodes in parallel on demand to process through the data. Each one of these is a compute task. And this is an interactive visualization of this dashboard, which is pulling data from object storage, reducing it through a MapReduce type operation, and is going to boil down that same figure of sea level rise that I showed at the beginning of my talk. So I'll just flip back over to the notebook here. And as soon as this line is done, we should be able to make that plot. So here we see this same plot of global mean sea level. So that was a whirlwind, but I am going to, I still want to keep sharing. I just want to go back to my presentation. So let's go back to this. So if you want to reproduce some of that for yourself, just check out those URLs there. So now I'm going to describe a little bit, having showed the demo, what is the Pangeo project, and how does all of this work? So Pangeo is first and foremost a community platform for big data geoscience. It consists of an open community, open source software, and open source infrastructure for actually deploying this stuff. We're funded by the National Science Foundation EarthCube program, NASA, and the Gordon and Betty Moore Foundation. So this community really consists of partners at a lot of different institutions, universities, government research labs, and quite a few groups from private industry. That's because I think we're working on a pretty generic technology stack that has applications in a wide range of fields. So if this appeals to you, you're all openly invited to participate in this community. We have a seminar. I'll skip over this part. So what about the software? So Pangeo software and the tools I just showed off in that demo really are part of this open source scientific Python ecosystem. And our approach, and I think this is a really important one, is to really try not to start a lot of new software projects and build a bunch of new stuff, but rather to take those existing community open source projects that are out there that already have users and a community around them, and try to connect them together and strengthen them and strengthen this ecosystem. And so Pangeo is really built out of Xarray, a computational library for gridded data, Dask, that distributed parallel computing library I mentioned that allowed us to scale our research out, Jupyter for interactive computing environments, and Zar, which is this cloud optimized storage format. And so, plugging all these things together, basically what we have is at the foundation, this cloud optimized storage format that allows us to put data very efficiently into object storage like Amazon S3. We have DAS, this general parallel computing framework that can run through Kubernetes or almost any other parallel computing scheduler. And then users just connecting to this type of system through a very lightweight web-based interface, such as Jupyter. I'm going to just skip some details here because I'm looking at the clock. The infrastructure we're running in the cloud really consists of two pretty separable parts. On one hand, we have a data library using this cloud optimized format, and we're storing data in a bunch of different locations: Amazon, Google Cloud, Wasabi, Open Storage Network. And then we have some computing hubs, Jupyter hubs and binders that are able to scale up and down on demand as users log in and out. This data catalog is really exciting and already exceeds a petabyte. Probably the most visible project we've done here is to partner with Google Cloud and bring the climate model intercomparison project data to Google's public dataset program. So putting over a petabyte of cloud optimized climate data in the hands of the world. Really important concept within this framework of bringing data to the cloud is the concept of what we call ARCO data, or analysis ready cloud optimized data. So what do I mean by analysis ready? That means we're not really so much thinking about sharing data files. We're trying to think about sharing data sets and hide that sort of complexity of, well, what are the files? How is this organized in files? So that researchers who use Pangeo in the cloud don't have to do that sort of tedious homogenizing and cleaning. They're already working with curated, cataloged data that's ready for analysis. By putting this in the cloud, we only have to do this one time. We don't have to have every scientist cleaning and organizing their own copy of the data. Another important part of this is the cloud optimized part, right? So cloud optimized data in the cloud, we're really talking about using object storage rather than file-based storage. And that means that the data format needs to play well with HTTP and support lazy access and intelligent subsetting over HTTP, and to integrate well with high-level analysis libraries and distributed frameworks. So using this type of analysis-ready data, I kind of already showed that, what we're able to achieve is really, really high processing throughput using on-demand computing. So what I'm showing here on the left is the sort of throughput we get as a function of the number of parallel processes using a legacy data server. And this sort of maxes out around 100 megabytes per second. Whereas if we're putting data in a cloud type storage, either within the same cloud, such as Google Cloud, or in Open Storage Network, which is a sort of edge cloud storage solution, we're getting data rates of 4-6 gigabytes per second, right? So orders of magnitude faster. And at that rate, you can really start to think about doing those, petabyte scale problems. So to kind of summarize, these are what I see as the 3 pillars of cloud native science: analysis ready, cloud optimized data, data proximate computing, and on-demand scalable distributed processing. So I would love to be just doing cloud native science all the time, but unfortunately there's some challenges that are preventing us from really sort of realizing this vision and fully moving into this. Pangeo has built some great prototypes, but we have not managed to sort of migrate our whole field into this way of working. And the 3 major challenges I see are sort of legacy data formats and the challenges those pose to migrating workflows to the cloud, storage and egress costs, which are institutions are rightfully worried about, and more generally just the funding models of who pays for this and who can access it. So in terms of legacy data formats, the problem here we've discovered is a lot of our traditional scientific data formats, such as HDF, FITS, Root, are not necessarily optimized for efficient access on cloud object storage. We do have some new formats, such as Parquet or ZAR, that are great on the cloud, but those aren't the formats that are generally distributed by data providers. And so we have this choice. Do we either reformat our data into some new weird format that no one trusts, or do we try to re-engineer the legacy formats? This is a kind of a big technical challenge. We're working on this in this project called Pangeo Forge, which is designed to sort of do data pipelines. So if you're looking to move some data into the cloud in a cloud optimized format, I would encourage you to check this out, and we'd love to work with you on this. The other challenge is that storage in the cloud is really expensive, actually. So to store a petabyte of data in S3 for a year, it costs $250,000. And just downloading that data out could cost $50,000. So that's a huge, people are really afraid of getting locked in. Here I'm really excited by these new innovative storage solutions that are sort of cloud compatible, but live outside of the main cloud computing sources. So Open Storage Network is one example of these, and we've been working with Open Storage Network and are really excited about that. Also, just from a few days ago, this announcement from Cloudflare, the networking provider, that now they have a storage solution to compete with Amazon S3 with no egress charges, called Cloudflare R2. So I'm pretty sure this is going to be a game changer for scientific data in the cloud as well. And then finally, we need to sort of figure out a funding model, right? I just heard, just before me, there was a great talk about the Hopkins HPC Center and what a big impact it's had. And I think it makes sense, you have a mandate to provide infrastructure for your institution and the people who work there, and there's a clear funding model for that. But since cloud infrastructure can kind of scale to accommodate anyone, there's no natural boundary to what a cloud computing resource can support. We could scale up our clusters to support thousands of users, the entire field. So who's supposed to pay at that point? So my hope is that we can sort of come up with some sort of franchisable situation where different groups, different institutions can sort of add capacity to a sort of federation of computing and data resources that are all networked together and provide high throughput interoperability between different sites, including traditional HPC centers. And I know that Alex and other people here have been working towards this type of vision for a sort of data fabric for science. So I think I've almost gone over time. I'll stop there. Pangeo, if you want to learn more about our project, we have a website, we have a forum. We're pretty active on GitHub and Twitter, and feel free to reach out and contact me directly as well if you have any questions. So thanks for the opportunity, and I'll stop there.
Thanks. Yeah, so please submit questions both to either to the Q&A or the chat. Thank you very much, Ryan, for the fantastic talk. Actually, until people gear up, I have a question. So you primarily worked in the Google Cloud, right? Or so how much different would be to scale or transfer the whole environment, for example, to Amazon or to Azure?
So Pangeo is deployed in all of those three main cloud providers in a pretty uniform way. So we're in Google Cloud because we just happen to have some credits there right now. But you may have heard of the Microsoft Planetary Computer project, which is a new sort of geospatial analysis solution in Azure, and it's really built on Pangeo. It's using this same foundation to provide scalability and data access. So Pangeo works in basically any place where you can run Kubernetes, or even places where you can't. So it's highly interoperable with the different cloud providers.
So you didn't have to do much tuning or anything?
I think Microsoft put, it depends completely on the Kubernetes performance, right? So Google's Kubernetes is the best because they invented Kubernetes.
Right.
Amazon is not bad. Azure has been playing catch up, but this is the standard interface that I think all these applications want to use to scale out.
Yeah. So any other question? Okay, so here is a question from Ali. So what is the biggest challenge for Pangeo Forge moving forward?
Well, Pangeo Forge hasn't really launched yet. It's kind of still, we're still developing it heavily. The goal there is to build a sort of crowdsourced data library, right? So we don't have to manually ingest data, but where science users can actually contribute these recipes for data that they want to have ingested and possibly transcoded or homogenized. And then the platform will go do that and stage the data and set it up and make it public. And so the challenge for Pangeo Forge is, can we achieve critical mass where we're going to actually have this really active sort of dynamic community of contributors? I think, it remains to be seen. We hope so, but whether people will really use it depends on how well it works and whether it meets their needs.
So another question is from Jaime. How do you see the government cloud use? There is lots of talk at the NSF, for example.
Yeah, and I would, like, in my world, I guess NOAA NOAA and NASA are both really proactively moving towards cloud. I've seen a big difference between, NASA is rebuilding their entire Earth science data platform in AWS. And NOAA is doing some similar things. But I think my impression is that they're doing a lot of things to support their operations in cloud, but they haven't necessarily worked out the piece of how are science users, individual research groups supposed to interact with cloud. So if I'm a NASA employee, I am part of a project, okay, we're going to use AWS to process our data. But what about the NASA funded scientists or even the non-funded scientists? How can they take advantage of cloud? Are we just going to use the cloud as a big, FTP server and everyone just download it back to their computers? That would be a waste. So I think someone really needs to advocate for the science users rather than just what the agency internal needs in terms of cloud. And Pangeo is trying to play that role as a sort of user-facing organization. NSF needs to figure out how they're going to allocate cloud credits. So NSF has this program called Cloud Bank that is pretty exciting. Right now it's kind of scoped just to the computer science directorate. But I think it's much better for us to be negotiating with the cloud providers at a large scale rather than each PI just going and putting the cloud bill on their credit card. But that's that requires quite high level coordination.
Yeah. So once again, thank you very much for this very dynamic, wonderful talk. And it was really showing us the journey we are doing. Thank you very much, Ryan. Again.
Thanks for the invitation.
Thank you. So let me then introduce our next speaker, Dr. Janis Taube. And Janis and I have been collaborating for the last 5 years very closely on cancer immunotherapy. So Dr. Janis Taube is a professor of dermatology and pathology at the Johns Hopkins University School of Medicine and a member of the Johns Hopkins Chemo Center. Her area of clinical expertise is dermatopathology. Dr. Taube serves as the director of the Division of Dermatopathology and as the assistant director of the Dermatoimmunology Laboratory at the School of Medicine. Dr. Taube received her undergraduate degree in engineering from Duke University. She earned her MD from Tulane University and her MSc in molecular medicine from the University College London. She completed her residency in pathology at Johns Hopkins, where she also served as the chief resident before undertaking a dermatopathology fellowship at Stanford University. In 2009, Dr. Taube returned to Johns Hopkins for her certification in the melanoma clinic. And I would like to note that she has just been awarded the George W. Hembrick MD professorship in dermatology and our chair. Congratulations, Janis, and welcome to IDEAS.
Thank you, Alex. It's a pleasure to be here and to share with everyone some of the work that Alex and I have been doing. Our main focus has really been on biomarker development for immunotherapeutic regimens, and together we've built what we call the AstroPath platform. And so, in full disclosure, we have relationships with Akoya Biosciences, and I'm going to be sharing images from their technology today. So in 2018, the Nobel Prize for Physiology or Medicine was awarded to Drs. Allison and Pangeo. And so previously there had been 3 pillars for cancer therapy, which we're all familiar with, surgery, radiation therapy, or some sort of anti-cancer drug like a chemotherapy or a targeted agent. And Allison and Pangeo were awarded for describing immune checkpoint therapy, which is really, rather than a direct assault on the tumor itself, like these other agents, it's an indirect way to hopefully eradicate your tumor. You galvanize the patient's immune system, which then secondarily goes on to kill the tumor. And so we still need biomarkers. There's been this remarkable success, and honestly, it's revolutionized cancer therapy. And yet the vast majority of patients still do not respond. So I work in melanoma and Merkel cell, and we're actually doing quite well with a 40 to 50% patient response rate. But there's other tumor types that are on the order of 10% response rate, if at all. And so certainly if you're a cancer patient with limited time, the goal is to match the right patient to the right therapy early on. Because of that secondary effect as well, there's delayed responders. So sometimes it takes longer to get different patients' immune systems going before the immune system goes on to attack the tumor. So you have to have the confidence that you've matched the patient appropriately to the therapy to let them sit on the therapy until that response gets going. A similar scenario can be seen, like the tumors when the immune system invades sometimes look like they're swelling on radiology or growing. And so you can have what we call pseudo-progression, where it looks like tumors are growing before they regress. And a biomarker, again, could give the provider the confidence to leave the patient on the regimen. You can even get new tumors developing on immunotherapy, which if that ever happened on chemotherapy, you would be pulled from the regimen immediately. But with immunotherapy, sometimes you're left on the regimen because sometimes these new tumors will blossom and then regress. There are so-called immune-related adverse events. At least that's what the pharma companies like to call them. You and I would call these side effects. And you can have these immune-mediated side effects. It's like an autoimmune disease where the body gets totally overactivated, and it can lead to destruction of the thyroid or hepatitis. Actually, on the original trial, there were a few patients who died from a colitis as well. Because not everybody responds to a single regimen, we're trying to come up with combinatorial regimens to see if that'll help, and having biomarkers could help, rather than combining everything with everything empirically, make a rational combination. And then, last but certainly not least, these are incredibly costly therapies. So a single regimen of checkpoint inhibitor therapy costs over $100,000. And so to protect the economies and also the healthcare system, again, it would be great to give these therapies to the patients who are most likely to get benefit from them. So we went to look at potential biomarker strategies. We can look for proteins that are expressed within the tumor microenvironment, and we do that by something called immunohistochemistry. So we looked for a protein that was the target or the ligand for one of the targets. That was one potential way to do it. You can look in terms of what genes are expressed in the tumor and see if that would be a good way to pick out who's likely to respond. You can look at the underlying tumor genomics, because ostensibly it's mutations in the tumor that leads to neoantigens being expressed that the immune system recognizes as non-self and can then go and help clear the tumor. There's also these emerging modality that we work in called multiplex immunohistochemistry or immunofluorescence, and that is mostly now a protein-based approach where you're looking at not a singular protein, but multiple expressions of proteins. And so when we were trying to figure out which direction we were going to go, we conducted a meta-analysis of the existing literature. And so we identified over 100 records through PubMed. We also did a search of meeting abstracts, and we screened all those, and we excluded the studies that weren't original, didn't have enough patients. We focused really on solid tumors. We left out leukemias and lymphomas. And in the end, we had 44 individual publications that were out there that included 55 different biomarker analyses. This was from more than 10 different tumor types and over 8,000 unique patient samples. And we essentially asked for each of these, what's the sensitivity and specificity? So for example, in this first chart, if you're looking at the underlying mutational burden in your tumor, your melanoma patients, assuming a given cut point, those above your threshold, how many of those were responders versus non-responders? And we use that to generate a sensitivity and a specificity for each report that was out there. Each report then gets a single spot here on this receiver operating characteristic curve. For those who don't work in diagnostics, the ideal test is in this upper left-hand corner where you have 100% sensitivity as well as specificity. And so, for example, these are all the studies that were out there that were looking at the protein target of a number of these drugs. And this spot or the dot size for each of the studies is proportionate to the number of patients that were enrolled. And so if you add all the other modalities on, these are the different spots. For example, the tumor mutation burden that we talked about is now shown in red. And so we then drew the receiver operating characteristic curve for both of these. We did it two different ways. We did it weighted by the number of patients enrolled in each study, or we did it where each study was weighted equally. And you're able to then estimate the area underneath the curve. Again, anything closer to 1.0 is your ideal test. And so essentially, whether you were looking at the DNA, the gene expression, or singular proteins, the performance was essentially the same, somewhere between 6.5 and 7 on average. this is really, a decent association, but if you're looking for a so-called companion diagnostic, one that if the patient has this marker, you then pair them to a given therapy, you want to have an area under the curve closer to 0.8. And of all these different modalities, the multiplex technologies were the only one that hit that key 0.8 threshold. The reason we think that this is important is because a lot of these, again, when they are measured as singular factors, are also measured in, if you will, the tissues taken and ground up into a milkshake, and then the genomics or the transcriptomics are done. It's not spatially resolved. There's no regard to which compartment is being analyzed within that tissue. And you also can't look at multiple cell expressions on a single cell. And so we think that that's really where the multiplex was gaining its diagnostic ability. And so attendant to that, we believe the next generation of biomarkers will depend on this quantification of multiple different cell types and their spatial interactions, and that we'll identify those using well-curated data sets. And so not surprisingly, the progression in biomarker development has really gone hand in hand with technological development. And a lot of the early presentations and papers using multiplex immunofluorescence only looked at 5 or 10 high-powered fields. And so what's a high-powered field for us in microscopy? This is each of the squares shown here of this lung cancer is a single high-powered field. And this single tumor had over 1,000 fields and took up over 30 gigabytes of disk space. And as someone who looks at tumors all day as a diagnostic pathologist, we read the whole slide. We don't read single high-powered field squares like this when we're prognosticating for a patient or staging a tumor. And it appeared as if we were really losing out all of the opportunity for this data. But also truly, I was concerned for sampling error. And yet I was crashing spreadsheets right and left and not able to move a file in terms of, off the imager to a server would take me 20 minutes. And I reached out to some of my mentors at the Cancer Center who thankfully knew Alex. And I was informed how stars and galaxies are like cells in pathology. And of course, that is indeed where we are. So you guys will recognize the astronomy viewer. Just by chance, on the right is the commercial pathology viewer that we use on a daily basis. And so similar functionality, we're organizing multicolored data, we're segmenting images, we're performing spatial statistics. And so this is one of the examples of an image that has been so-called phenotyped. Each of the cells in this image have been assigned a lineage. And you can see that obviously cell quantification would be facilitated as well as distance metrics between cell types. One of the functionalities that had not yet been studied with these technologies was whether you could reproducibly look at intensity on individual cells. Functionally, we think this is really important. Cells express proteins at different levels, and it can tell you about the state of a cell. It can tell you when a cell is just coming in, an immune cell, and starting to attack tumor, versus once the attack is over and the cell is so-called exhausted. That can all be measured if you can actually measure intensity. And so through a number of optical corrections and normalizations, Alex was able to help us generate robust measurements of marker intensity in situ. And so this flat 2D image on the left is what you typically see with our multiplex images. But here's the scenario that I described before. these cells that are shown in blue are expressing PD-1 at low to mid levels on this 3D plot. And this is when the T cells are just starting to get going and coming into the tumor. And then as they make their way into the tumor, they're spent, they're exhausted, and they express PD-1 at very high levels. And in fact, this is a biomarker consequence. If you simply looked at PD-1 positive versus negative, you might be counting these exhausted T cells as well. And in fact, therapy will not help recover these. The anti-PD-1 based therapies only recover those that are expressing PD-1 at low and mid levels. So this is what we want to be detecting for biomarker purposes. And now with this accurate imaging are able to do so. So we were able to map with single cell accuracy tumors, just like I described, in immune cells as they went into and out of the tumor and expressed these molecules on their surface in different ways. One of the cool things that we found was a new phenotype that had previously been unrecognized or underappreciated. So cells that express this molecule FOXP3 are called suppressive T cells. So when you get your immune system going, there has to be an off switch as well. It's what keeps your liver from consuming itself after you have the flu, right? You fight the virus and then you have to turn off the immune response. And so FOXP3 positive cells are known as suppressive cells, and they often express this marker called CD4. And so when folks had seen CD8 FOXP3 positive cells, they thought it was just a different flavor of the same suppressive family. In fact, we were actually able to show that instead of being a suppressive cell, this was an early activated cell that was very cytotoxic and very powerful in the anti-tumor response. And we were able to map that to the leading edge of the tumor. There are also a number of outstanding questions. I mentioned that, we really didn't have the capacity, nor did anybody else, to map the whole tumor using these technologies. So people had developed their own strategies. Some people most who had a background in immunotherapy would go for so-called hot spots where the immune system was interacting with the tumor, and thinking that that would be the place, of course, to study these interactions. Other folks felt strongly that you needed to do representative sampling. So looking at the edge of the tumor, the central aspect, to look at areas that were inflamed and non-inflamed. And the fact that with Alex's help, we were able to image the entire tumor and survey it the same way that you guys had surveyed the sky with overlapping field tiles and reassembly allowed us to ask important questions about which sampling strategy was best. We were also able to identify certain groups of cells that predicted poor patient outcome, those patients that had the best outcome after a couple of years, and those with an intermediate prognosis. And so I would break these in a very practical sense. Those with the good prognosis, great, they're on the right therapy. Those with the intermediate prognosis probably need some sort of combination with their immunotherapy. And then those with the poor prognosis probably should be on something other than immunotherapy. And we talked about those ROC curves. What we actually were able to do with the multiplex, once we had optimized the tumor microenvironment sampling, which by the way was hotspot, had the biggest diagnostic impact. Our AUCs were above that 0.8 threshold at 0.92 in both a discovery and a completely independent validation cohort. And here are those three phenotypes that I had pointed out before. So for those who aren't used to looking at this, this is overall survival, and this is the proportion of patients that are alive after 5 years. So for the patients who had that good prognostic phenotype, 90% of them were alive at 5 years. and meaning we put the right patient on the right therapy in that group from before they even started. So these are pre-treatment tumor specimens that we're looking at. And again, the same stratification between good, intermediate, and poor was seen in the validation cohort as well. We got to ask questions like which sample, not just whether representative or hotspot sampling was better, but how much of the tumor microenvironment did you need to sample for better biomarker performance? And the answer using the tiles was 30% of the TME. We were able to drop out markers to see, did you really need 6 markers or could you achieve similar efficacy with less? And the answer was actually 6 was great. Did we need that intensity metric that we worked so hard to achieve? Yes, we did. If you actually didn't read these as low, middle, high expressors and only had them as positive or negative, you didn't get the same diagnostic resolution. And we were able to look at specimen size. It's always important to think of adequacy. You know, would a needle biopsy that gets stuck into a tumor be the same as if a patient had surgery and had a whole metastasis removed? And in fact, you could use small specimens is equally as good as large specimens using the biomarker that we developed. So we've really developed a unique facility that's capable of producing petabytes of robust tissue imaging data. The discovery and validation cohorts that I showed you guys for melanoma had over 72 million individual cells mapped. And we've now expanded to numerous, not just pre-treatment specimens, but also on-treatment specimens in a bunch of different tumors. We're adding genomic information in as well as spatial transcriptomic data. And for those that are familiar with the Cancer Genome Atlas, we've been able to secure the slides from the TCGA data set, and we'll be mapping those specimens. And we'll be able then to have spatial protein coordination to all of that other wonderful correlative data. Our plan now is to increase the number of markers that we're looking at by performing multiple stains on sequential sections of tumors, each of which are 4 microns thick, and then Z-stacking them. So we think that we're going to be able to get somewhere between 27, 28 markers across a whole tumor section. One of the other things that has been under development is a wonderful website called CellView, which is interactive, and we hope to launch that. This is certainly, again, looks a lot to the Sky server in terms of functionality and inspiration. Here's just a still image from that website. This is a tumor that's been treated by immunotherapy, and this blue line is where the tumor used to be. The green line is where the tumor is now. So you can see maybe 2/3 of the tumor has regressed, and we're able then to map the different cell types in the regression bed and see what I like to call the immunoarchitecture, how the immune cells have to be organized to facilitate that tumor regression. And we hope that that'll lead us to a better understanding for treating those patients who are still resistant to therapy. And with that, I would like to thank everyone, especially a number of the members of the IDEAS team that I probably don't get to thank enough and who are valuable contributors to this work. Thank you. And thanks, Alex, again, for the opportunity to present.
Thanks a lot, Janis, for this wonderful presentation. And it was really at the perfect level for physicists as well. So for a very broad audience, thank you very much. Okay, so questions. So while people type, so what would be the next science fiction-like goal that you would like to see happen?
we've talked about some of these. I think the idea would be to really integrate the genomic and transcriptomic features in such a way that we're able to map those across an entire tumor section. We can certainly do them, again, singular fields, so you have protein expression in one broad axis, but a low level of numbers. And right now, transcriptomics is a very high level of transcripts studied for a very small focus, but it would be incredible to be able to broaden that and to be able to link which cells those transcriptomics are coming from. I think another wonderful thing to do would be able to map tumors longitudinally as they progress. I think we'd get a lot of insights into how tumors avoid the immune system, and to do that in a meaningful number of patients and in tumor types would be really a game changer for the field.
Yeah, so thank you very much, Janis, again for the wonderful talk. So thank you. So, and with this, I think I'm handing off to someone else who will moderate the next part, the student awards.
Yep, I can take it from here, Alex. Thanks.
Yeah, thank you.
All right, good afternoon, everyone. I'm Tara Engel. I'm the administrative manager for IDEAS. And one of the programs I've really enjoyed helping IDEAS bring to fruition is the Student Summer Fellowship Program, which offers or invites undergraduate students at Hopkins to submit proposals for a 10-week research project over the summer, in which they partner with one of our IDEAS faculty members and design a data science focused project. And so today we have two of our 2021 awardees to share a little bit about their projects from this past summer. So starting things for us today is Jaxon Wu. He's studying history of science, medicine, and technology. And his mentors this summer were Jonathan Weiner and Shintan Pandya from the Bloomberg School of Public Health. So with that, I will hand it over to Jaxon.
Thank you, Tara. I'm just going to share a screen here. Awesome. So as we know, the past year and a half has been a challenging one for public health. From all the tension and turmoil we have experienced, perhaps the most glaring of which come from the socioeconomic inequalities that have become ever more so recognized as a significant contributor to health disparities here in the US. To improve health equity at the individual and population level, the healthcare sector must play a pivotal role in identifying and addressing the social risk factors and needs of individuals. And here is where we come in. Our project, Humanizing Our Data, is the first step towards developing a social needs measure that enhances risk stratification of a population to further advance state-of-the-art predictive modeling tools for high-risk case detection. The purpose of our work is to identify the prevalence of the social determinants of health, SDOH needs in Medicaid population covered by the Johns Hopkins healthcare community, captured in both administrative claims and electronic health record data, and to assess the impact of these individual SDOH needs on healthcare utilization and expenditures. Since the Medicaid population, that is over 75 million, of America's poorest and most vulnerable have significantly higher SDOH needs compared to other patient populations, it is unsurprising that a growing number of states are implementing tools to capture SDOH in their Medicaid population, while also developing and incentivizing interventions to address some of these SDOH needs, including covering community-based services and integrating SDOH in performance measurement and managed care rate setting tools. However, there are ongoing gaps and challenges in identifying the vulnerable or high-risk population with SDOH needs using these existing standardizations and what constitutes SDOH and how to classify these factors. Our project uses the relatively more accepted framework of International Classification of Disease, version 10 Z codes, also known as ICD-10 Z codes, to identify SDOH needs in patients. Hence, to comparing the prevalence of the use of ICD-10 Z codes to identify SDOH needs in the Medicaid population in claims versus EHR data is important because it gives us the opportunity to develop a more consistent way to identify high-risk target population for interventions. And on top of that, understanding the overlap of these social needs captured in each data source may enable us to more effectively identify high-risk population with specific social needs, leveraging both the data sources for population health management intervention, as well as risk adjustment activities. So with all this in mind, our study has two key aims. First, we sought to explore the prevalence of ICD-10 social needs in administrative claims and EHR data of a Medicaid population. And second, we aim to assess the impact of these ICD-10 social needs on healthcare utilization, narrowly defined as the amount of emergency department visits and inpatient hospitalizations, as well as healthcare expenditures captured through total healthcare costs, pharmacy, as well as medical costs of our Medicaid population. So how did we achieve our goals? Upon importing the raw data from Priority Partners' continually enrolled Medicaid population claims and EHR data sets from January 2018 to 2019, we found that our baseline study populations was 305,000 with continuous enrollment throughout the 2 years. We had a EHR data set about 449,000 patients. Enrollees who were older than 65 were excluded due to the unavailability of their Medicare claims data. Moreover, enrollees that did not have any outpatient visits in 2018 were also excluded as they would not have any diagnosis codes in claims to assess their health status or social needs. As you can see, the final study sample here was around 39,000. So beginning with our main independent variables of interest, the social needs marker we created was a binary variable suggesting the presence or absence of any of the 5 social needs domains captured in ICD-10 Z codes from our 2018 claims data set. Each of these 5 social needs domains were separate, had a separate marker with the yes/no indicator suggesting the presence or absence of any corresponding mapped ICD-10 codes to the 13 social needs subdomains. A count variable of 0, 1, or more than 1 was also created to identify the total number of social needs domains present for an individual. Each of the social needs variables were created from the 2018 data set separately for claims EHR and a combined claims EHR data set we created ourselves. And now the dependent variables were derived from claims data in years 2018 and 2019, including 0 or more than 1 emergency department visits or 0 more than or equal to 1 hospitalization counts. So cost variables include total cost, medical cost, and pharmacy costs, as I discussed. And due to the high skewness, cost variables were Windsorized at the top 1% to avoid undue impact of outliers on our estimates. So aside from the social needs variables, our other covariates included age, sex, hospital dominant morbidity count, ADG count, and ACG risk scores that were extracted and tidied from the respective ACG claims and EHR outputs. These covariates would be derived from the 2018 claims dataset only. So in our retrospective cohort study, we defined the social needs marker as a documentation of ICD-10 codes in any of the 5 social needs domains. And the impact of these social needs markers were compared across 2 diagnosis-based, that is the demographic as well as Hopkins's proprietary diagnostic predictive model scores, models using concurrent and prospective predictive models for any occurrence of emergency department visits or hospitalizations, as well as total medical and pharmacy costs. To achieve our first aim, our patient population and their respective social needs domains were analyzed across 3 data sets, claims and EHRs, as we received from our original data source, as well as a combined claims plus EHR data set created ourselves. We then first sought to create a summary of the patient characteristics and prevalence of these social needs in 2018 and 2019 to get a comparison across those with and without social needs ICD codes in the 3 data sets. Next, concurrent and prospective models for assessing the impact of these social needs in both years on healthcare utilization and healthcare costs were created using logistic regression to predict hospitalization and DD visits, as well as linear models for total pharmacy as well as medical costs. After controlling for covariates in 2018, regression models were finally compared across the 3 data sources of ICD-10 codes for each of the healthcare utilization and cost outcomes derived from claims data in 2018 and 2019. And moreover, we found the top 10 ICD-10 codes based on frequency and the top 5 codes within each of the 5 domains. So a snippet of what we found is that the prevalence of social needs markers in our study population increased after combining data sources, resulting in 11%, 13%, and 18% of the patients with documented social need ICD codes across claims EHR and claims EHR respectively. Another significant finding is that our combined data set of claims and EHR captures 51% of those of African American descent, much higher than the typical rate found in the American population. Also, as well, adding social needs variables to demographic only models improve predictions for all utilization and cost variables. In the diagnostic predictive risk model, social needs marginally improve the outcome predictions. So no significant improvement in prediction we're seeing across the 3 data source of the social needs markers. So to wrap up here, we demonstrated the feasibility of using EHR and claims to systematically capture social needs, which could modestly augment predictive models of healthcare utilization and costs in non-elderly Medicaid population, and enable managed care organizations to undertake risk assessment and adjustment to develop effective population health interventions and policies. The next stage of my project will focus on including unstructured data such as free text electronic health records, as well as Medicare/commercially insured populations. Moreover, we will be looking to add geo-derived information so we can identify patients who live in neighborhoods with high risk of SDOH issues such as food deserts, and compare how neighborhood issues match to individual issues recorded in the EHR, thus assessing how effectively SDOH needs are captured. Results from these projects will be used to help screen and identify patients with unmet social needs, which can then be used by healthcare organizations to target populations positioned to benefit from specific clinical, population, and policy interventions. And with that, I'd like to thank IDEAS and Taube again for this amazing opportunity to engage in population health analytics with CFIT. And thank you everyone for listening.
Great, thanks so much, Jaxon. That was a great presentation. If anyone has any quick questions for Jaxon, if you just want to put them in the chat. I guess while we're waiting to see if anyone has questions, Jaxon, what was your biggest takeaway from doing this project this summer?
I think my biggest takeaway with this project technically was the amount of data cleaning and tidying needed to be done, even though we were working with structured EHR data. Getting the data with like millions upon millions of variables, finding and extracting what was important may sound intuitive, but the actual work needed to get done, as well as the domain knowledge to understand what these data points are trying to tell us relating to our patients was a learning curve, but also a very rewarding one in the end.
Very good. All right. Okay, well, I don't see any questions, so thank you again. And we'll turn it over to our other awardee who's here today, Shengwei Zhang. He's studying applied mathematics and statistics, and his mentors for his projects were Tinglong Dai in Carey Business School and Kimia Gobadi in the Whiting School of Engineering. So with that, Shengwei, I'll hand it over to you.
Thank you, Tara. I'm gonna share my screen. Okay. So hi everyone, my name is Shengwei Zhang. I am an undergraduate student at Hopkins, affiliated with Malone Center for Engineering in Healthcare. Today I'd like to share a series of research projects I have been working on in operating room scheduling optimization. Specifically, we developed a OR scheduling tool using data-driven approach, and part of this project was done through the IDEAS Summer Student Fellowship. This project is in collaboration with the Johns Hopkins Hospital, and my faculty mentors are Dr. Kimia Gobadi from Whiting School of Engineering and Dr. Ting Long Dai from Carey Business School. Okay, so first I want to give some context of this problem. Operating rooms are one of the main resources in hospitals, and any disruption in their workflow can have a cascade effect on the rest of hospital operations. There has been a growing interest in optimizing OR schedule in hospital management. However, many of those work only consider a portion of the perioperative process, and one underdeveloped area is designing a OR scheduling system that effectively improves the overall efficiency. So the complexities in designing such a system come from the various perioperative input. There are three types of inputs. The first one is the surgical features from patient's EHR data, which give the OR schedulers the basic information of the case, patient, and procedure. The second input is the OR administrative rules, which put some constraints on the surgeon using the OR in certain manner. And the third input is the post-operative capacity constraints, which involve downstream facilities such as PACU, ICU, and surgical bed. So our work focuses on using data-driven approach to integrate all three inputs into the OR scheduling process to ensure a smooth patient flow. So I'd like to introduce the framework of this OR scheduling tool to give you a general picture of this work. So the foundation of this tool is a OR scheduling model, which is formulated as a mixed integer program that schedules incoming surgical cases to certain OR and time slot. The model takes input from three different modules, including master block schedule, incoming surgical case features, and daily surgical bed census focus. Now we use Groby solver to solve this model and output a case schedule with multiple objectives. After each scheduling iteration, the remaining OR capacity and surgical bed capacity are updated to reflect cases already scheduled and prepare parameters for the next model run. Further, we define some metrics to evaluate how good the schedule is. And this presentation will focus on how we optimize the three input modules using data-driven approaches, such as machine learning and survival analysis. So let's first discuss the input modules on pre-operative information. The first input is the pre-specified OR information queried from master block schedule, including the OR operating hours and OR in-block surgical service. So basically, the in-block surgical service tells us which OR on which day is scheduled for which OR service. The second input is the surgical case features queried from hospital Epic data warehouse, which include case surgical service, time window, patient class, and surgeon estimated case duration. One thing we observed from this data is that surgeon estimate duration is usually not accurate, while this input is crucial to our OR scheduling model. So we are motivated to query more patient-related and procedure-related features and build a predictive model for this input. We trained the prediction model with the 12-month historical surgical encounters. We developed two types of candidate models, all-inclusive model that train on all available features, and service-specific model that trains individual models for each OR service. For each model type, we applied three machine learning algorithms, random forest, XGBoosting, and linear regression. Then we test the candidate models on the test set and compare the results with the surgeon's estimation. The evaluation metrics are R-squared, mean absolute percent error, and the accuracy. The conclusion here is that the service-specific models all perform better than all-inclusive models, and XGBoosting slightly outperforms other algorithms. Then we select the candidate models to be deployed. For each OR service, we select the algorithm that has the best prediction accuracy. And in this manner, we are able to improve the prediction accuracy for 19 OR services out of 44 compared to surgeon's estimation. Next, we discussed the input modules on the surgical census focus. So surgical inpatients are usually admitted to downstream surgical beds after surgery for several days of medical care before getting discharged. Therefore, the surgical census level will put reverse constraints on the OR scheduling process, and we are motivated to develop a predictive model that provides dynamically changing daily surgical census focus based on the current scheduled case volume. So in order to predict the daily surgical census, we can decompose it to the individual contributions. We can predict the individual patient's length of stay in the hospital. And to predict the patient length of stay, we can predict the patient discharge probability per day. So this problem falls into the domain of survival analysis. Survival analysis is a time to event method, and in our setting, the event we would like to predict is patient being discharged from the hospital. This model can give a discharge probability per day, and 1 minus that probability is the patient's census contribution per day. So we train the model with 12 months historical elective surgeries and their length of stay. 2 survival analysis models are generated, one using the OR service as the predictor and the other using OR procedure. The output of these 2 models are 2 census contribution files for each service and procedure. As you can see in this table, for service cardiac surgery, the length of stay index range from 0 to 14, and the census contribution monotonically decreasing from 1 to 0. And the table for procedure muscle biopsy is similar. Later, we can match the incoming surgical case census contribution with service or procedure and calculate the case contribution in the next 14 days. We apply a moving window method to validate this model. We did 26 iterations, and each iteration tests on 2-week data. As you can see on the right, the actual census are all in the 95% prediction interval in each iteration. And the final result shows that the OR procedure model performs slightly better and is integrated into our scheduling tool. So after going through how we optimize the input modules in this framework, I should talk about the OR scheduling model. But due to the time limit of this presentation, I will skip this section and go directly to our result. So we evaluate the output case schedule through a 4-month OR scheduling simulation. We collected historical elective cases operated in 1 OR site with 6 rooms. Then we run the proposed scheduling tool on this case set and output a new schedule in the same period. We compare the proposed schedule after optimization with the original one on the average elective utilization rate. We present 2 figures here, one using estimated duration and the other using actual duration for measurement. Although our scheduling model uses the estimated duration as the input parameter, the 2 figures shows the average utilization rate of each room are similar, which demonstrates the effectiveness of the previously defined case duration prediction model. And in both figures, the highlight is that the proposed schedule increased the average utilization by around 14%. Then another metric is to compare the daily surgical census utilization of the 2 schedules. The cap is set as 40 beds per day, and you can see that the census is only decreasing in these red dots in the left graph, which are the weekends that we do not schedule patients, but some patients are getting discharged during the weekend. So this is kind of mimicking the real census graph you will see in the hospital. And the main takeaway from this is that the proposed schedule has a lower standard deviation, which can help smooth the fluctuation in downstream surgical bed. So that's all for my presentation today. And right now we are drafting a paper for this project and also collaborating with the hospital on the implementation step. Please let me know if you have any comments, and we really appreciate that. Thank you so much for listening, and thank you to IDIES for this opportunity to present my work.
Great, thanks so much, Shengwei. I'll give you the same question I gave Jaxon, just while we see if anyone has any questions they want to ask you now. What was your biggest takeaway from your project this summer?
Yeah, so I think during this summer, I had the opportunity to deeply interact with the clinicians and the perioperative leaders in the Johns Hopkins Hospital, which is really some experience that I won't get during classes at Hopkins, right? So I think this is really a great experience for me to know how data science is utilized in the industry and how what kind of methods can help them improve their daily operations in the hospital.
Great, thank you so much. All right, so I don't see any questions right now, so I'm going to hand it off to Ani Thakar, who is our IDEAS Director of Operations, to do our closing remarks.
All right, thank you very much. Let me share my screen. Okay, can you see that?
Yep, sorry.
Okay. So, well, I think everybody must be numb by now, but I just wanted to say a few words about what we've learned and where we go from here. So I think some of the emerging themes were no surprise. Machine learning is ubiquitous in data science. Cloud computing for scientific data and server-side analysis are the big takeaways, I think. We've seen exciting work in terms of machine learning with deep learning, active learning, as well as predictive modeling. We've seen everything from supernovae to nanotech, quantum computing, cancer immunotherapy, so a broad range of different types of application domains. And I hope there's been some healthy cross-pollination and people can get some ideas from what they saw over the past 2 days. We also have seen some diverse use cases for SciServer, which I think can become an excellent stepping stone to using commercial clouds. I think we could do some more in terms of how we facilitate elastic scaling. And I think it's clear that IDEAS partnerships are increasing across disciplines and technologies, so that's a really good sign. Let me just take a quick minute to introduce and recognize the core team that keeps IDEAS ticking on a daily basis. And these two clouds here, basically, one is the developers cloud and the other is the IT team. And as you can see, our admin manager, Tara, is just floating above the two clouds, effortlessly managing everything. So in the development team, there's quite a large team we have, with Gerard Lemson being in charge of the science direction for IDEAS and for SciServer. I'm in charge of operations. We have a communication specialist, Jordan. We have developers who specialize in different aspects of the applications that we provide services for. So there's Manu, there's Dimitri, Eric. We have a machine learning specialist, Adi. Jaywan is specializes in user interfaces and outreach and other aspects. We have some young, bright postdocs, Heshi and Maggie. We also have Steve, who is working on the medical campus for us remotely, Steve Handy. We have a database group with a database expert, our resident database expert, Sue Werner. And we have two DBAs, database administrators, Victor and Ying. And in the IT group, led by Brian, we have Lance, Jason, and Kyle, who keep everything running. And they're the people who usually answer questions to IDEAS help. Just quickly looking at the year in review, it's been a difficult year. We survived COVID relatively unscathed. We lost a dear colleague, Jan Vandenberg, to cancer. I'll say a little bit more at the end. The IDEAS family had a new baby. SciServer made some new strides with installations in different types of application domains, from NIST, Max Planck, National Astronomical Observatory of Japan, PMAP here at Hopkins in the School of Medicine. We introduced the Robbins Awards and the Student Fellowship Awards gathered steam this over the past year. SDSS 5, the latest instance of the Sloan Digital Sky Survey, got underway. And IDEAS was a co-sponsor at the MedHacks 2021 hackathon, which is, I think, the largest medical hackathon. And thanks to some of the people who had to work very hard for this, Maggie, Jordan, Heshi, and sorry, I misspelled the name here, and Herard. Looking forward, there's still quite a bit of work to do in increasing our profile within Hopkins for both IDEAS and SciServer. We do have several new people joining soon, so these are exciting developments. We have developers, Michael, Amir, and soon a UI specialist, we hope. We have a communication specialist joining soon, Kate Stevens. And then we are going to be hiring a few more IT people. Machine learning and the artificial intelligence initiative will be our increasing focus in the near future. And I hope, we said this last year too, but this time we really mean it. Next year we'll be able to go back to having the symposium in person. So let me just say thanks to all the speakers, the poster presenters, all the attendees. Thank you very much. And of course, the organizers. This year, Tara and Jordan had to do it all by themselves, and they did a wonderful job. So thanks again, Tara and Jordan. And I'd like to end on a personal note. Once again, we lost Jan Vandenberg, our systems architect, over the past year, and he was like a big brother to us, both figuratively and literally. He used to watch over our services and be the first one to notify us if anything went down. And we learned so much from him, and he was always a great inspiration, and we miss him every single day. So I'll end with that, and hopefully we'll see you in person next year. Thanks everyone. Thank you very much. Jordan, do you want to wrap things up, or that's it?
Yeah, no, I think you did a great job of closing. Thanks for coming, everybody. Thanks to Tara. I did a little bit of work. She did probably 90% of the work. And you did a great job, Tara. Thank you. And thanks for coming. And we hope to see you in person next year, everybody.
Thanks, everyone. Thanks, Jordan and Ani.